adding some specific column vector to each column, okay, specific numbers. And such a matrix is non-singular, you already know, and it also has the second property. Then the original matrix A itself is non-singular. And what is the purpose of this one? When you write down no. When you write down let me remove that nonsense. Then again, okay. I think I'll take the actual paper itself. Okay. How do I push it down? Okay. So that is the lemma, okay? So in some sense, if you have, this is the next, see, somehow we have to work to show order field properties maintained in this class, okay? That means we have to show, so these are the intermediate lemmas. For example, if the rational function is of the type Pt over Qt, Pt and Qt are two polynomials, and the rational function Rt is Pt over Qt. Well defined in some interval. Suppose if Rt is a rational number for all rational t, then Rt is of the form P star t over Q star t, where P star and Q star are polynomials with rational coefficients. The coefficients are also rational. See, for example, if you take a continuous function, which is rational at all rational points, okay? And you only know it's a continuous function, it's rational at all rational points. Does it mean it is a rational function? It takes rational values at rational points. So if you take, for example, fx equals absolute value of x, it takes rational values at rational points, and it is only a continuous function. But here you have to say it's a rational function which is taking rational values at rational points, but P and Q are now polynomials. So you can manipulate with the degree and induction on the degree to show that you can rewrite the same thing in terms of another pair of rational functions with this special property. It has to do more with the degree stuff. And how is the, okay, this is, okay, this is nothing. Okay, we can leave that. How the matrix lemma is used, see, the Shapley equation, when you write it down, it is of this type. You have an immediate reward R Sij plus beta transition from state S to S prime, B beta S prime. The value of this matrix game is the value of the stochastic game. Okay? In the case of a stochastic game, single controller stochastic game. But then the crucial thing is you can use Snow-Shapley theorem to characterize an extreme optimal pair. The optimal strategies of this dummy game gives you these optimal stationary strategies of the stochastic game. So the extreme optimals, when you have to think about, Extreme optimals are characterized by a square subsystem. Of the given original matrix, you can choose a square subsystem with the two strategies are equalizers. So when you do that one, we can look for some subset. For each beta, you have a different subset. Okay? If you fix a beta, then you have one square submatrix. If you change the beta, it can be another square submatrix. But there are only finitely many square submatrices. Therefore, for betas sufficiently close to 1, it will be the same thing. Okay? That's the idea. And then the other thing is, in fact, the entire thing in stochastic games, for a general stochastic games, even for the zero-sum case, the most difficult thing is 1 minus beta times V beta. That limit exists in some strange sense. It is quite difficult to prove this in the general case. And that is where Tarski's decision theory, etc., are used by Kohlberg first. First Kohlberg did it, but later Mertens and Neyman also did it, and there was a PhD student by name Monash. And the story is Monash approached, he was a student of Gleason, and then he casually met Elon Kohlberg and asked him, do you have any interesting problem in game theory? So Kohlberg suggested, here is this problem. And Monash tried to dash it off, and then there were lots of errors here and there, because he was just a student, okay? But he didn't care much for the thing. He wanted to wind up and get a job somewhere else. And then later, these people polished everything and made the clean affair of the whole thing. So, if the state space and the two action spaces are finite, and if the transition probabilities are controlled by one player, then in the sense of the limiting average payoff, the actual value exists. Further, the value and a pair of optimal stationary strategies have components that lie in the same Archimedean ordered subfield. Because you could have also had, we have to remember, even people like Hermann Weyl and even von Neumann, in his days, even though they proved the minimax theorem, he proved the minimax theorem, but he struggled hard to find an efficient way of solving for the value. So he developed all kinds of differential equations and whatnot. Hermann Weyl came, and he came with the idea of basically working with simplexes. But it was only when, I'm forgetting even the Danzig, when he talked to von Neumann was orally dictating to him what is the duality theorem. Okay, and that became quite central for the whole field in some sense. Okay. In the case of non-cooperative games, again for the 2%, okay, they wouldn't, yeah, okay. There what happens is, I said one minute, let me remove this. How do I? Oh yeah, I do this. Okay. Let me, then I. Okay. 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 Wait, just a minute. Okay. Okay. This is the 1 minute. Match. Okay. So when you look at the discounted single control non-zero sum game, you are playing the only player 2, for example, controls in all states. Player 2 controls in all states. Then you write down the two matrices A as just in terms of the immediate payoff for player 1. Okay? Sum of that. And for the other player who controls the transition, you take actually the discounted payoff. And when you write down any mixed Nash equilibrium of this bimatrix game, the theorem is we can recover the Nash equilibrium of the stochastic game through just the Nash equilibrium of this bimatrix game. And when I didn't go through the proof of this, because the proof is only a technical thing, okay? I said that we struggled hard with the Lotus program in those days and finally came with these answers, everything. But interestingly, why should we be concerned only with Nash equilibrium? Why not with correlated equilibrium? Okay. In correlated equilibrium, intuitively what it really says is, you have a referee who chooses, suppose you are given a bimetric game. A referee chooses one of these entries with a fixed probability. And this probability distribution is informed to the two players. I am going to select one of these entries with this specific probability distribution. I myself do not know where I will end up because after all, I am only performing the experiment with this probability distribution. But the only thing which I will do is, the moment I end at an entry, say ij, player 1 will be informed about the I part. You choose row I. The other player is told you choose column j. Player 1 is told you choose column I, row I. Player 2 is told choose column j. Suppose these two informations are given, each player can now think as follows. Why should I choose what he said? I can choose something else also. But I do not know what was given to the other player. Okay? I do not know what was given to the other player. Assume if the other player is somebody who obeys the judge or the then I can evaluate assuming that he is going to obey the judge and choose exactly what he would have said, then I can calculate, because I am given I am player 1. If I am given I, then I can evaluate conditional probability that he was given J. Agreed? So you can evaluate the conditional expectation of this one. So the conditional expectation by obeying the judge for me is better than deviating from this. The new conditional expectation, in this, the conditional expectation part is the same. It's only the entries are changed. Then that doesn't gain anything better. If that is the case, then it is a correlated. If both players believe in it, then it is a correlated equilibrium. This was the concept introduced by Bob Bauman. And the advantage is the class of correlated equilibrium is essentially defined by linear inequalities. So it's a convex polyhedral set. In the case of two-person case, you have extreme points. Those are called the extreme correlated equilibrium points. You also have what is called extreme Nash equilibrium points. What do you mean by extreme Nash equilibrium points? Nash equilibrium may be quite a complicated set. You take any maximal convex subset of it and then look for the extreme points of them. Okay? Every extreme point of any maximal convex set contained in the Nash equilibrium set is called an extreme Nash equilibrium point. Now, a theorem which I proved with one of my students, Evangelist Hervé, is that there is an extreme correlated equilibrium which is also a Nash equilibrium. So what we tried to do was, there was an intuitive theorem by Pradeep Dubey which said that by and large the Nash equilibria are inefficient. Or inefficient in some sense. It's worse in some sense. So what we tried to do was we tried to minimize players 1's correlated payoff. And it picked the answer in no time. And that answer was the same answer as what I have here. That's what happened. Okay. This I didn't draw the picture. Okay. These are unnecessary. Okay. This was one of the state space. We have taken all the time only state space finite. So you can take the state space countable, you can take the state space uncountable. So stochastic game, the vast theory is there. Lot more theory is there. But when it comes to algorithm, you have only a few of them right now. Okay? So when I took my talk as algorithm, it was essentially over. Okay? When it becomes then the only way it can be improved, I can prolong the talk only by explaining every places where I had some intuition of kind. Let me okay. So the Markov decision process with arbitrary state space was concerned by Don Ornstein and showed that if the optimal return function is bounded and if the state space is countable, then in a positive dynamic programming problem, optimizer has positive means every entry, every time you receive positive income and you are taking the total. You're taking the total. But after a while, suppose the total is nothing is added, then it's a bounded case. Okay. So what he showed was in positive dynamic programming problems, the optimizer has an epsilon optimal pure stationary strategy. That's what he was able to show. And Raghavan pointed out that if player 1 controls the law of motion, Ornstein's theorem extends to positive stochastic games. Further, sufficient conditions for the existence of epsilon optimal stationaries were given. But unfortunately, we constructed a counterexample showing that Ornstein's theorem cannot be extended to positive stochastic games with general transition functions. Okay. Here is an example. You have countable states and assume the state 0 is absorbing. 1 and 2 have only 2 actions. If the game is in state S, if player 2 chooses the first column, then it moves to state S minus 1. That's all it happens. If it chooses the second column, it moves to S plus 1. Okay? But if player 1 chooses the second row, then if he chooses the first column, the game is absorbed. Nothing happens. If he chooses the second row and the other person chooses second column, you get 1 and move next time to, depending on whether he chooses the first column or second column. That's how it is. So when this game, we try to show that the value exists and the value is at least half. In fact, the only question which David Blackwell had in mind was, we were working with Tom Ferguson, who was also visiting us, with myself and Novak and Ferguson. And then I said, your own example with Blackwell should be the source for even a counterexample. He didn't believe it. But later, when Blackwell said, I like everything, but what is the value of this positive stochastic game? And Bs is S plus 1 over 2S. And then that's what we showed. And we used some strange, I don't have the paper with me here. I was looking for the paper. I don't have the paper with me, but it was some beautiful inequality of Lagrange in Bromwich's book on infinite series. We noticed, and that was the main key theorem to be used to prove this result. So what this game has is, to play intelligently, you not only have to depend on where you are, but where you started. Okay? They are called semi-stationary strategies. A strategy is semi-stationary if it depends on the state where you started and where you are now. It's always a function of that. Okay. So that's where this whole thing finished. I have only two possibilities. I can talk about a possible application of stochastic games to tax evasion. Okay? And that's all I can do for today. If it continues tomorrow also, then I talk. Otherwise, I can talk about algorithms for cooperative games, especially for special class of cooperative games, very simple class, for which I can locate the nucleolus, how to locate the nucleolus. Okay? So that's what I want to talk in case I have the time for the other one. Okay? Now, let me start with what is our tax evasion problem? PJ. I don't know. No. Just a minute. Okay, my son sent this is what it is. Yeah, he sent this. Okay. I don't know. That is not. Just a minute. Let's see the Maria, see whether it is there inside. Ah, maybe that. Okay. How do I keep? Yeah. Okay. See, you can think of tax filing as a game between Internal Revenue Service and the taxpayer. Why the tax game is zero sum? How to detect evasion via discriminant analysis? The need for a game theoretic refinement, a simple model of the tax return audit game, the generalized stochastic game with incomplete information, games with lack of information on one side, SGLIOS. It is a single control sum game with lack of information on one side, etc. Norms for audit and should they be public? A single control game with incomplete information. All these things are okay. Here, one can model tax evasion as a zero-sum 2% stochastic game with incomplete information. We can incorporate the classical statistical classification to classify a random observation from a mixed population. It captures the secrecy of the tax office and the lack of information about the past history of the taxpayer. With full information, the model is quite close to structured class of stochastic games that admit efficient algorithms for optimal solutions. In the beginning, tax evasion was considered purely as a utility maximization problem by the taxpayer. Okay. And then there were works by Reingarnham and Bilday, Davis, Hecht, and Perkins, and so many people have worked on these things. Okay. Secrecy behind the audit procedures of the tax office and lack of full information about any taxpayer and his possible evasion strategies. These aspects have not been effectively incorporated in public economics literature. To get closed-form equilibria, model builders tend to make drastic assumptions. We do not look for closed-form solutions. We look for models that retain incomplete information and secrecy of actions while staying close to stochastic game models for which efficient solutions exist. Okay. Now the taxpayer is given, player 2 is a taxpayer in a given socio-economic group. The taxpayer by choice or by ignorance of the tax laws adopts a strategy to evade taxes on selected taxable items. You see, there are several items on which one has to pay the tax and how to get away from it. Based on the socio-economic group, the IRS holds a prior perception of the taxpayers' methods and modes. They have some working knowledge of them. What happened was, I tried to submit this as a research proposal to the Internal Revenue Service. They were ready to fund it, actually. All they wanted was, please send me your citizenship card and this and that. I said, I am an Indian citizen. Oh, we are sorry. We cannot help you. But I can send you all the kind of technical information which we use for tax purposes. So they sent me what is called DIF, which is using discriminant analysis to classify people, whether they are cheaters or non-cheaters, whether they are continuous cheaters like that. Okay. A stochastic game whose transition law and states are unknown to player 2, but known to player 1. Most economic models are non-zero sum. Tax collection is a conspicuous exception. The IRS must collect all that is due from individuals, small firms and corporations, and in addition, remove iniquities, ensure each taxpayer pays no more and no less than his rightful share, use machinery and manpower efficiently. While millions of people are submitting their taxes, there are only a certain number of officers who can attend to this problem. So they have to make a choice who are all going to be, whose tax forms are to be selected for intensive look. Okay. Or modify continuously improve collection procedures. Now, what is legally due is also unclear without expert advice. The tax burden ought to reduce the large disparities of income and net wealth produced by the market economy. Those who do not fully believe in the tax laws develop passive resistance, varying levels of evasion through loopholes. Petty merchants who do not report all sales receipts retains the sales tax. Customers share the pie by buying goods cheaply without sales tax. Things like that are happening everywhere. Individual returns were classified for audit exclusively manually before 1963. Only about a quarter of returns filed were screened to keep classification cost bounded. With a limited personnel, the IRS could act on only a small proportion. Lack of full information about the taxpayer plus secrecy of auditing procedures implies tax collection is ideally suited to the game theoretic nature. Expected values gain meaning under repetition because the same guy is going to be submitting next year's tax also. In a sense, you can watch this person's tax submission year after year. So the taxpayer population itself is heterogeneous, but if people in a professional group move among their own and inherit similar socioeconomic patterns. Stratify, therefore, by profession. So the by executives, doctors, lawyers, salesmen, and professors and external. Returns that are legally correct and honest versus legally incorrect or manipulated. It can be legally incorrect or it can be due to manipulation. Nearly 25% of returns were on the second type in early 40s. Deductions were under 12% of reported income in 47, 15% a decade later. A foolproof audit on persons in a profession targeted earlier, norms so that conspicuous violations become audit candidates. Audit an honest cost, an honest return implies auditor's time is wasted. If I audit unnecessarily an honest taxpayer, you have wasted the time. Fail to audit a manipulated return implies loss of tax properly due to the tax office. So now you can think of a tax return as a vector x whose coordinates are tax items. Say x1 may be married or single, x2 may be gross income, blah, blah, blah. Okay? That's a classification. Some qualitative, some quantitative. For simplicity, take all of them as quantitative. Now, past data from the two subpopulations adjusted for inflation gives means, variances, and covariances. So you can have the densities, you can think of the two densities as F1x and F2x of the two populations. If normal, they are determined by their mean vector and covariance, variance covariance matrix. Suppose RRC is a partition of observations into don't audit, audit, with prior probabilities xi equals xi1, xi2. With this probability, you select somebody and then you decide to audit or not audit. The expected cost can be written like that, and the whole idea is to minimize by keeping the integrand negative, and this is all part of Fisher's work on linear discriminant analysis. And this is equivalent to the intuitive reading. Each tax item I with reported value xi carries a certain weight wi. If summation wi xi is greater than c, don't audit. If it is less than or equal to c, audit is suggested. Even though it is suggested, you may not be necessarily auditing. Cost coefficients, prior distribution, etc. are difficult to compute exactly. Many hard estimation problems surround them. Suppose doctors and hospitals are pressurized by federal regulation to charge a fixed amount for a diagnostic treatment. Income of the profession is much affected. Lifestyle cannot be changed easily. So temptation to evade increases. If you screw up some people, they have temptation to evade increases. Patterns of expenditure do not adjust immediately. The priors themselves change over time. We need models to analyze this. Okay. So we will refine the discriminant function approach by formulating multi-stage game models that capture the essence of the game. Okay. Two players play one of the games A or B, and this is the usual. If I am trying to explain it to a tax office, this is what I would say. Okay. Now, the Shapley's theorem gives you the value, and with discounted value, etc. Okay. Suppose past auditing gives the IRS the hunch that 10% manipulate their returns and 90% are honest. So given a return X, IRS can compute the discriminant function, which decides whether to audit or not audit. But the IRS also has an initial perception that can override the discriminant function. Okay? That perception varies from year to year depending on the past. This year's data may not reveal it, only last year's perception gives the clue. Perception is the state of the game. Only an audit can change the perception. So that means the state of the game is the perception of the IRS office. Even where the discriminant function favors auditing, staff shortages may prevent it, which implies strategic selection of audit is the only alternative. If a return is not audited, the perception, what is the perception change? There is no perception change. Okay? It will be the same as last year's. So you can think of each tax file, you put them into different boxes. First box, these are all the tax files of last year contain in the first box, say that these people, according to the IRS, are honest people. So somebody has been audited and that person has made a mistake or something, whatever it is. So this perception changes. So he is pushed into the next year's, at the end of the year, it is pushed into the second box. So you have like that box after box, depending on the level of the perception. Okay. Credibility is maintained until an audit proves otherwise. You are always giving the benefit of doubt to the person till they find something wrong with you. The threat of audit must always be present to discourage future manipulation. Okay. So, in fact, what happened is, I'm just telling also the story of the whole thing in some sense. In parlor games, the immediate rewards are defined by the rules of the game. In modeling a real problem, coming to grips with a meaningful payoff is itself a major hurdle. What is a payoff in a particular social game in itself is a complex problem. And then I was working with a biologist, Gary Hyatt, at UIC. And then what happened was he had large collection of combats, animal combats. That means crabs, fiddler crabs. They were all fighting for burrows. What happens is when you have low tide, the crabs, male crabs, some of them find themselves into little holes. The female crabs, they are looking for convenient houses. You can think of them as nice houses for, so if the boy has a nice house, so this crab has an interest in that boy. That's how it is. Okay? And then sometimes the crab which is looking for a hole can go and fight with the other crab. But what is fighting? In the case of real fighting, we know how to use a gun and this and that. They have only signals. And even biologists have a lot of problem of understanding those signals. But over the years, they have found certain type of signal means this fellow is the loser. So they both, final result is they go down push and one of them comes out. The which comes out, maybe the guy heavier or the guy lighter, it can be. So the biologist said the whole complex data collected. And he has the data, but he doesn't know what to do. His whole question was whether they are programmed to play intelligently. Whether they are programmed to play intelligently. So then I tried to model it as a differential game and some such thing. And then used the differential game approach to interpret this data, whether it is consistent with the solution of the differential game model. You can only do chi-square test to do that, and through the chi-square test, we found it nice. And then Maynard Smith himself visited the UAC. So I met him and we had a long discussion. And he was telling, this is the serious problem is payoff. That's what he said. But so in some sense, it's the same thing happens also here. So estimating the prior perception of probabilities, you can have a rough overestimate of the proportion who would have manipulated through such inequalities. Okay. All standard existence theorem assume full information about past history. So the definition of the generalized stochastic game, you have a population pi partitioned by player 2 into subpopulations pi 1 pi n. Player 2 selects secretly pi j and draws a random observation x from pi j. X is revealed to player 1. Independently, one partitions pi into p1 pn with a fixed prior and initially selects pj secretly according to psi. Given x, whose source pi j is unknown to 1, player 1 computes j is the set of actions available. And he chooses secretly one of the actions and receives from 2 the reward Rxia, and the game moves from pi to pk with this probability. Future payoffs are discounted and player 1 maximizes and player 2 minimizes. So the game object, tax interpretation, we have such a setup. The importance of discriminant function lies not just in classifying the observation, but in suggesting possible audit actions from the current data. That's the important thing. What are stationary strategies and things like that go on? Does the generalized beta discounted stochastic game admit a stationary optimal strategy? Many of them are still unknown. We do not know. Okay. When x comes from a continuous densities corresponding to pi 1 pi n, and the conditions of problem 6.1 hold, can stationary strategies, mixed stationary strategies be replaced by pure strategy, a single action for each perception PS, equivalent in the sense of equal rewards. Okay? And this is closely related to the theorem of Dworetzky-Walden-Wolfowitz. You have a finite parameter set, which are called the states of nature. You have a finite number of action set, and f omega a continuous density for each omega, d the space of decisions of the sample space, and L a bounded measurable loss function, then any randomized decision can be replaced by a pure decision. So this is equivalent to saying, when you are doing testing a hypothesis, you want to test the hypothesis whether F1 is true or F2 is true. When you want to do this one, and if you specify type 1 error and type 2 error, etc., you can only find one, and you may first, to do this one, you partition the sample space into two parts. But why should you use this particular sample space? You may have different partitions and select one of them. Okay? But when you have continuous densities, it is enough to stick to only one partition. And that is the idea of Dworetzky-Walden-Wolfowitz theorem, and which I noticed was also done by Blackwell. I noticed that. So this is, we are asking to extend this theorem to the setting of generalized stochastic games. The tax return audit problem is a statistical extension of stochastic games with incomplete information. Okay. Incomplete information was pioneered by Harsani and given precise models by Oman and Maschler. And stochastic games with lack of information on one side was studied by Melo Lidakis, a student of uh, Tom Ferguson. You have a set of n states, identified states as, you have a prior distribution, a law of motion Qt Sij. The game moves to T from S when row I and column J are chosen secretly in state S with immediate payoff. Player 1 alone knows the true state. The choice Ij are revealed to both after being made. The immediate payoff is kept secret from player 2, though known to player 1. Payoff is discounted. Melo-Lidakis theorem is that gamma be a beta discounted stochastic game of type this. One can associate an ordinary stochastic game gamma star in which player 1 has a pure optimal stationary strategy F star xi and player 2 has a stationary optimal strategy G star xi. In gamma star, player 1 uses his usual information in selecting his behavioral strategy, but unlike in gamma, 2 is informed of the posterior distribution at each state based on the state, the player's actions, and the law of motion. And his main theorem is V gamma is V gamma star. One loses nothing by revealing the posterior. So it goes on and on like that. So this is only a model. So can the norms for auditing tax returns be made public? Volatile but valuable to examine through suitable models. In our game with incomplete, if the state alone is kept secret, but not the law of motion. So anything, as soon as you add one more complication, lack of information, it becomes quite a difficult problem. I really do not know much about how to go about it, but at this age, I will not be able to make any progress. I think only a younger generation can get an idea of reading this and try to think originally. I wish them the best of luck. I stop here. Okay. Tomorrow, I think I will talk about what is the problem. I just state the problem. Okay. You have n boys and n girls. Each boy can say, I like this girl, I like this girl, I don't like this girl, blah, blah, based on looks or moving with them or whatever it is. Similarly, each girl can also say the same thing about various boys. Now, you can pair them together as long as mutually each one likes each other. Otherwise, you say you cannot pair them. So if you pair them, you put a 1. If the ith boy likes the jth girl and the jth girl also likes the ith boy, you put Aij as 1. The matrix, this is a matrix of zeros and ones. Now, suppose the diagonal of this matrix, 1, all of them are 1. So in theory, first girl can be matched with the first boy, second with second, nth with nth. So my question is, after the marriage, this is only before the marriage was done, they are married, okay. Who is the dominating person between the two? Okay. So this is the thing which I want to talk about. How do you measure the domination power? Game theoretically. And can we kind of compute the dominating strength in some meaningful way. And that was, in fact, it was based on an earlier work of myself with Thomas Solmosi on assignment games. Regularly, we were studying assignment games and algorithm to solve assignment games in terms of its nucleolus. So that's what I would talk tomorrow. Instead of, I would stop with the stochastic game has a lot of theory. So theory means my constraint was I was supposed to talk only on the algorithm or computational side of it. So it doesn't make much sense to go further into the theory. Okay. So on the algorithm, why you may say, why I am interested in algorithm. I want to also say a little, I had a professor by name Professor K.R. Parthasarathi, who was a brilliant probabilist. And we used to constantly talk about mathematics in Indian Statistical Institute. He was explaining to me every continuous function in the interval 0 to 1 can be approximated uniformly by polynomials. And he explicitly showed me how to construct the Bernstein polynomial. And then it was a very happy thing. I learnt it. And then I came to a paper by Bonsall, a British functional analyst. He had a theorem. Suppose you have a continuous function which is non-negative at the origin, then you can not only approximate it by polynomials, you can choose the polynomials of the type a0 minus a1t plus a2t squared, etc. Alternate in sign kind. And then I said, here is that theorem. I said, it's very interesting. Parthasarathi was very angry with me. I give you the function ft is equal to t. It is non-negative at the origin and it is continuous. Construct the polynomials of the type which you mentioned. I didn't know how to construct it. I still do not know how to construct it even now. But I have read the theorem. I explained the theorem to him. He wouldn't believe. Then it took some time for me to slowly convince him that it has more to do with weak topology. Okay? And then for convex sets, weak closure and strong closure are same. So these are the key ideas, and it is purely an existence theorem. There is no constructive proof. So ever since he said, try to work on problems with a constructive proof. That is how I was kind of always moving away from pure theory to constructive proofs. I believe in constructive proofs only in some sense. Okay? So constructive proofs and algorithms, that appeals to me in that sense. Okay, thank you.
slide sans dessus.
Ah non, justement, je sais pas où le mettre.
Ah,
si
mais
tu fais le...
je sais que c'est sur le côté là.
Ah, d'accord.
Mais ils vont. Attends, est-ce qu'il y a quelqu'un là-haut?
Ben oui, c'est ça, je sais
Il n'y a
pas.
pas quelqu'un parce que c'est samedi. C'est parce que c'est
Ben, je pense que
dedans, à
oui,
l'intérieur,
d'accord.
c'est un peu tricky.
Ah bon.
Mais il y a des jeunes qui sont là. On peut leur demander. D'ailleurs,
D'accord,
ils sont
non, mais
dehors.
attends, de toute façon,
Attends.
c'est à 5 que ça commence.
Oui, puis en plus, il va falloir attendre un tout petit peu parce que, je dirais, les gens sont toujours
Ouais,
lents.
ouais,
Et
ouais.
comme il y en a
Mais
beaucoup,
il y aura peut-être quelqu'un puisque c'est enregistré, paraît-il. Donc,
Oui,
peut-être même
oui.
pas enregistré.
Et là, le truc, c'est qu'il faut aller, c'est
Ah,
ça.
c'est derrière.
C'est derrière, comme ça,
Ah oui, je vois.
dans cette direction.
Je vois. Alors, des fois, il y a un sens.
D'ailleurs, moi, je vais faire la même chose parce que
Ouais.
j'ai aussi mes deux trucs à mettre.
Ouais. Si ça
Alors,
s'allume. Voilà.
là, tu devrais
Il y a,
voir.
génial. Je vais le copier parce que quand on le copie pas, ça m'est arrivé. C'est l'horreur. C'est bon.
CTRL L.
Je vais voir si ça marche. Alors, contrôle. Ça marche de moins en moins sous contrôle L. Ça, je préfère pas y toucher. Je vais dire non. Je sais pas ce que c'est. Bon, bah, écoute, ça, je l'attendrai. Écoute, le principal, c'est fait. Assignat électroconducteur. Bon, bah, écoute, j'attends.
Ouais.
Je te laisse, tu peux le faire.
Oui, je vais mettre le mien. On peut
Voilà.
minimiser là ton truc juste une seconde.
Oui, pas trop quand même.
Non, juste un peu.
Je
Oui, je suis
plaisante.
comme toi. Je suis
Je
très
plaisante parce que des fois, ça va.
très prudent. Là-haut,
Voilà.
là-haut, juste
Non, mais
là-haut.
là, je le ferme. Voilà, normalement.
Ah, ok. Ah,
Bon, attends. Là, j'ai peur de tout fermer. On va voir. Non, tu vois, regarde, là, je préfère pas
ouais, il
cancel.
vaut mieux minimiser.
Ouais. Dis-moi, toi qui parles espagnol, tu comprends peut-être le portugais. Donc, mais tu sais, tu peux le mettre, hein, tu peux la mettre, ta disc on keys. Hein. Ben oui, ben ça marche pas.
Ah.
Non. Attends, je remets le mien.
Don't break it. Il est pénible ce truc.
Voilà.
Oui.
Moi, j'ai pas pris de précaution pour le.
Non, ça...
Normalement, il vaut mieux.
Non, ça marche pas. Ok, esta herramienta. No, but... No, ah, bah, c'est quoi? C'est un PDF? Non. C'est pas un PDF, non? C'est un PDF, hein? C'est quoi? C'est ça?
Oui, c'est celui-là. Ouais, regarde PDF.
Ah ouais, c'est un PDF, mais c'est étrange que ça marche pas.
Qu'est-ce qui marche
voilà.
pas?
Contrôle L.
Voilà. Ah, génial.
Est-ce que tu peux encore minimiser là pour que... Oui. Parce que si je mets mon truc, je ne veux pas déranger ça. Escape. Ouais. Ah, voilà. Okay. Mais attends. Fais attention, si ça ne marche pas, c'est parce qu'hier, tu vois, dans mon séminaire, c'était un truc.
Oui, tu as eu plein de problèmes, toi.
Mais je ne sais pas pourquoi. Mais c'est ça.
Ouais. Ah, mais des fois, on peut le faire à la main.
À la main, oui, mais je ne savais pas que c'était ce truc. Donc, tu essayes avec ça.
Donc, à la fin, tu le faisais à la main?
À la main, oui. Mais non, mais tu essayes avec ça, parce que ça allait démarcher. Mais si ça ne marche pas, c'est...
D'accord, ok, merci.
Alors, j'essaye de faire la même chose.
C'est pas compliqué,
oui.
J'y suis arrivée.
Avec moi, la barre est faible. C'est celui du haut, c'est le...
N'importe lequel, à mon avis.
Ah, d'accord.
Moi, j'ai pris celui qui était à ma hauteur.
Ah, ben voilà, ça marche.
Mais tu vois. Côté cours.
Oui, c'était les autres qui le faisaient. you want to use it mobile? Yeah. Good morning, everybody. Thank you for surviving the conference and showing that it's still alive and kicking. It's my great pleasure to introduce the next speaker, Gabrielle Demange. Gabrielle, I'm sorry, but I feel I owe to these people to reveal for how long I've known you. And now it doesn't count in years, it counts in fractions of century. It's all essentially half a century. So according to Al Roth's metric, it's before we were born, I mean, by a long margin. Anyway, yes, indeed. I mean, you have had a very long and productive career. What I appreciate particularly in it, I mean, is the fact that, you know, along with the fundamental theoretical contributions, there were a lot of results which really pushed the frontier of applications of game theory and Mathicon elsewhere through fundamental work with Marilda and David Gale and so forth, and many other things. In particular, also network. I still remember very, very much, of course, very fondly the first work you did on single peak preference over networks, which was very, very creative and has been also noted. So without much, I don't need to say more about you, and we are happy to listen to you for 50 minutes.
Okay. Thank you very much. Thank you very much for this nice introduction and for being here on a Saturday morning. So I will talk today, yes, it works, of communication between individuals when they are communicate through a social network. And what I want to talk is about the duality in decisions. Very often when you communicate, there are at least two types of activity. And the one sometimes you could think is active, the other one is passive, but this is not the way I see it. Let me give an example. For example, on online social media, you post contributions, but you react to others' contributions, okay? And similarly in research, one publishes and one reads other papers, okay? So this is what I call dual activities, and usually there is a positive feedback between them. And this is what I want to study. And when you think, you find that this type of duality in many situations like friendship or education, okay? So my objective is to develop games to study this type of mutually reinforcing decisions when individuals are on a network. So what I mean by network means that they communicate through the network, only with the neighbors. So this is what is called now a game on network, which means that the actions you take depend on the actions of your neighbors and may influence the action of their neighbors directly. But indirectly, it might be affected by the actions of the neighbors of your neighbors and so on. And this is typically this type of phenomena that one wants to study when one studies a game on a network, okay? So maybe I try this one. And yeah, so the questions, I have two types of questions, or related, but so how does the joint determination of cost contribution, now I will use this term, content production, and attention shapes the communication and influence, which is kind of fashionable word. And the second point is more related to the studies, existing studies on games on networks. And so what are the relevant tools? And in particular, is it still the case that some indices known as centrality, which are basically eigenvectors or power indices in a network. If you don't understand, it's not important, but they are easy to compute. And they have been introduced in sociology and much used in now by computer scientists in large networks, because they have access to large networks and have the ability to compute these indices. And it turns out that these indices are meaningful in some games with a single action, especially I thought I had the reference, a game by Ballester, Calvo, Amengo, and Zenu. So I will study these two types of questions in two benchmark settings that differ in how attention is allocated. And I use this terminology of social media, but you can translate into other contexts. So the main features are, I have a follower influencer network. It is given, so I am not considering how it is formed. And so individuals post contributions, and they are accessible to all their followers, which means that there is no congestion. This means that basically you can see it as a local public good. And there are two types, as I said. I will consider two games. One where players, followers dedicate attention or differentiate attention, which means that they may pay attention differently according to their followers. And undedicated attention, where they choose a general level of attention. And so the results, I mean, the analysis differ a lot depending on the two settings. So dedicated attention, and I will mainly speak about this one. And there is a very rich equilibrium analysis. And what I like is that you have multiple equilibria, but they are interpretable. They can be described and quite easily interpreted, and because each equilibrium is characterized by an endogenous formation of disjoint interacting groups. So at the end, of course, I can always consider that the network is connected. So in principle, everybody could communicate indirectly, but when you have these disjoint interacting groups, this means that communication is cut from some of the agents. And some equilibria, which I will call stars equilibria, display a very unequal distribution of attention. And I find this result interesting because there are studies which show that this type of phenomena where some influencers are local stars. So it gives some micro foundation to sometimes what is called rich get richer phenomena. But so here it's an equilibrium. So it's not a kind of ad hoc imitation behavior. So in undedicated attention is much more easy to study because it's very close to the model that have been studied with one single action. So there is a unique explicit equilibrium, except if their spillovers are so large that actions explode. And so this means that one interest is that you can study some policy recommendations or policy interventions, and I hope I have time, but you have many. For example, Twitter, I mean, one of the reasons of the success of Twitter was its recommendation system, where it recommends new links or new friends to people. Okay, so, and from a more technical point of view, here I mean, the analysis is related with some tools that have been introduced, again, by sociologists and computer science in now in two-mode networks. And one is called projection and power indices appropriate for what I say two-mode networks is a two-sided network. And I'll come back to that. So there are some empirical studies that show, I just have little reference that shows this two-way interaction between attention increase contribution and contribution increase attention. So it has been first shown at the macro level, but now you have more micro level. And so one paper, I mean, which at least was, I found very interesting, so it's not necessarily what I have written here, is an analysis of the Twitter follow graph, which show that influence, which is measured in this paper by the number of retweets. You know, you tweet, and the more your tweet is retweeted is considered as a mark of attention, and so, or influence. It is related, but not so much with the degrees or with centrality indices, actually. Okay? So this means that, I mean, observing the network is not enough to derive behavior or influence. And this is why, in some sense, you need an analysis, or you need an analysis of a game on the networks may be interesting. So I recommend this paper also because it shows it was the beginning of Twitter, and they show that their Twitter was used like they decompose in some sense, but not really mathematically. They showed that there were two kinds of networks, actually. One between friends who communicate both ways, and one between experts or influencers and followers. And this second one, actually, at the end, was the main role of Twitter as a media of dissemination that disseminate information. Okay, so now, so what I will do is I introduce the games, so the networks and action. Then most of my talk will be on the game with dedicated attention, and then the game with undedicated attention. So I have a network, I denote by G. So an edge Fj means that F follows J and or has access to the post of J, and J or J influences F. Okay, so I will talk here only on, I will assume the network is bipartite, so, or two-sided or two modes, so it's the same. And, but actually the results extend to non-bipartite, to general network. So bipartite means that an agent is either a follower or an influencer. You have two disjoint sets, okay? When you have a general network, I mean, you may be both a follower and an influencer. So result extend when you have, under some assumption on preferences. So, but you observe actually you observe bipartite networks, like for example, traditional media, where you have readers on one side and newspapers or journalists on the other side. Or politics, actually, also education or traditional education, where students are supposed to listen to teachers who teach. Okay, so each influencer posts contribution. So since an influencer is a female and a follower a male, it's easier to do it that way. And so an influencer posts contributions, BI. It can be a number, it can be, you can think in terms of quality. And her payoff depends positively on the attention that she receives. Not only her payoff, but also her incentives to post contribution. And each follower pays attention, and his payoff depends positively on his influencer contributions. So when I consider dedicated attention, this means that the follower F chooses a level of attention, AFJ, for each influencer J. When it is undedicated, it is a single level. Okay? So just, it's a really silly example, but just a very simple network. So here, F3 is the only one to have two influencers, I1 and I2. I don't need to put an arrow because I assume my network is bipartite. So implicitly, all the arrows are directed from F to I. And so if attention is dedicated, F3 can choose a different level of attention to I1 than to I2. Okay, and this is not the case if it is undedicated. So payoff. Payoff, I mean, I put it in a footnote because it's like in the Ballester, Calvo, Mengel, Zenou. Payoff for an influencer is quadratic. And then the important thing is that you derive a best response that is linear. So it is linear, so this means that the contribution of I is a fixed amount, which is I's characteristic. Sometimes people call it the standalone characteristic because it is a level of contribution that you would take if nobody pays attention to you. It's a minimum level. And then the more you receive attention, so it is a sum of the attention you receive, the sum of the F that follows I mean, your contribution increases. And how much it increases depends on a parameter which I call the impact factor of attention on contribution. So it is positive because otherwise, I mean, you have no feedback from attention to contribution. B bar I? Delta is a constant, yeah. So it's the same for constant also across agents, yeah. That's true. And so followers payoff is a little more complicated with dedicated attention because so now you F chooses AFJ, okay? So it has the same form in the sense that it's a linear return on paying attention, but now you have a linear return for which depends on BJ. Okay, so and the cost is depends on the sum of the attention that F pays. Okay, so again you have a parameter which is the same for all followers, so the impact factor of contribution on attention, and a characteristic, a personal characteristic. Okay. All the examples I will show you, I will assume that the characteristics are the same across followers or influencers. So this is what I call homogeneous characteristic, but it's not important. Okay. So what it implies, this is important, is that the follower's best response is no longer linear and no longer monotone. Why? Because what happens is that the attention now, the total attention is determined, but it depends on the maximum of the contribution of the influencers of F. And F allocated attention only to the influencer, his influencer with maximal contribution. Okay, so this is okay. You have a bunch of choice and you choose the one that are the best. And the best one, if there are several, I mean, you are indifferent between them and you allocate your total between them. Okay, which is a feature actually which is often observed, more or less up to some noise. Okay, so from a point of view of the analysis, it has an important impact. It means that you have no longer strategic complementarities because when the contributions of the influencer increase, you may switch from one to another one, depending on how much, I mean, they increase, the relative increase, okay? And this means that actually you cannot rely on iterated best responses, and the equilibria might not be ordered, okay? And so this is different from game. Most games on networks with a single action have strategic complementarities. Like the first one was Maurice with 0-1 action, and BCZ with quadratic, and I had a paper with more general utility functions. So maybe I switch this one, and I will come back to it later. It was an example to show why you may have multiple equilibria which are not ordered. Okay, I mean, it's so how do one find the equilibria? And basically, the main remark, not really a remark, but it's that it is very important to know who pays attention to whom. By that, I mean that you may pay no attention to one of your followers, which means that AFJ may be null. And so in that case, null attention results in cuts in the network. And even if your general network is connected, which I assume, you can always assume that your network is connected, and then the network of attention, which is formed with the links where you delete the links where F does not pay attention to J, so you obtain a subnetwork which might not be connected, okay? And this network then, I mean, is decomposed into components. And this is why I mean, you may find an equilibrium where you have groups that do not communicate between each other, okay, because of these cuts. Yeah. No. Yeah, I have already quite, yeah. Maybe there are some, but I did not, yeah. Anyway, you allocate your well, maybe I don't want to enter, yeah. So basically, I show that a network is essentially characterized by the network of attention, by its network of attention. So given the attention, I can derive the network of attention, essentially because sometimes in very rare you may have an indetermination of attention, the allocation of attention, but the payoffs are the same. And but of course, not all subnetworks of J can be an attention network of an equilibrium. So basically, this means that to search for an equilibrium, you should search for the attention network that supports an equilibrium. Okay? So I will consider actually two types of, mainly, but token, of specific equilibrium. Equilibrium one where the network of attention is the full network. So everybody pays attention to all his influencers. And other equilibria of the stars equilibria. Okay? But before, I need to consider what I call isolated pair. You can see them as component of a subnetwork, but it's not necessarily a component. And I want to define a spillover measure in that pair, okay? Because as I said before, in a game on a network, what really matters in equilibria are the spillovers. I mean, how the actions spread and how much does this increase possibly actions, even though I have not full strategic complementarities. Okay, so isolated pair, it's simple. I take a subset of follower and a subset of influencers, such that each follower in S has at least one influencer in T. Okay? And what I mean by isolate, I isolate pair because I cut all the edges from S to influencer outside T, or from T to followers outside S. Okay, so I have a small network, and I call delta the product of the impact factor. I call it the compounded factor. Okay, because as we will see, I mean, what matters is the repeated feedback, and it will depend on this product. Okay. So spillover effects, so I consider this isolated pair. If there exists an equilibrium within an isolated pair, maybe it does not exist, such that, or maybe each influencer in T contributes the same amount, I call that uniform amount. Then a first condition to have this equilibrium is that the ratio of the number of followers per number of influencers is not too high, but it is affected by this component factor. So it's a necessary condition. For people who know the model with a single action, you always, because you have linear best responses in the standard model, you need to bound, in some sense, this feedback. And this is why, I mean, delta must not be too high. The second condition, and we have this one, such type of condition. The other is that B is completely determined, and it is equal, basically, to an expression which depends on the characteristic per influencer. So it is the average of the characteristic of the follower multiplied by their impact plus the characteristic of the influencer. But you divide that by the number of influencers times an expression which I will call the spillover measure. And because the first condition is satisfied, this expression is bounded. Okay? So this means that basically this amount at equilibrium multiplies the characteristics by the spillover measure. Okay? And this spillover measure is really important to understand why you may have several equilibria, is that it comes from the feedback between dual actions, and the more followers you have per influencer, the more important, when you increase their action, it has an influence on the contribution. Okay, this is why you find this ratio. And so it does not depend on characteristics. And not only it's increasing, but it is also convex. So you have really a kind of snowball effect when you have more followers. Okay? And furthermore, the closer this delta times the ratio is close to 1, the less important the characteristic. So this means that the network or the links becomes more and more important. Okay? So, as I say, I consider equilibria with extreme attention, and I start with the one with full support. So the equilibrium attention network is the full network. Everybody, every follower pays attention to each of his influencers. And I just needed some notation, is that for a subset S, I consider the set of influencers of S. And I denote that by G plus of S. And the equilibrium condition bears on these pairs formed with S and all the influencers. So I state when the preferences are homogeneous, but the result is true, I mean, takes a different form, I can say, when you have no homogeneous characteristic. So in that case, so there is an equilibrium with full support if and only if for each subset of F, or subset of followers, the condition that limits spillovers are true within these pairs formed with S and the influencers of S. And furthermore, this ratio, so which must be small enough, but which also depend on delta, but the ratio for the cardinality, number of followers over number of their influencers, must be the largest for the whole set of agents. Okay? So what is important is that the second condition bears on the network. Whatever delta, it does not depend on delta. The first condition, spillover, you decrease delta, it is, okay. And so it relies on an existence of a feasible flow. So the second condition, when you have no homogeneous characteristic, basically it says that if a pair S, G plus of S, the influencer, isolate themselves and play the uniform contribution within the pair, this contribution is smaller than the one for the whole set. Okay? So, in some cases, if it were the case, they would be better off. Okay? You could think they would block. But here, it's just a Nash equilibrium. But you find that at this Nash equilibrium, no group has incentives to isolate themselves. Okay? So an example, for example, here I have, if I take for S, F3, F4, and F5, I have 3 followers, and they all have a unique influencer, which is I3. Okay? And so this means that the ratio I need to consider is equal to 3. But the overall ratio in the population is 5/2, which is less than 3. So there is no equilibrium with full support. Okay? And one can understand easily by hand why it is the case, because we are sure that I2, even if F2 pay attention only to I1, I2 will receive more attention, and the contribution of I2 will be larger than that of I1, and so F2 should pay attention to I2. So in this case, it's very easy to understand. Okay? So I skip that. So stars equilibrium, it's one where my components, my network of attention is formed with collection of stars. How much time I have? Wow, okay, perfect. And so the followers are partitioned into sets of followers, subset of followers. And in each subset Fm, all followers in Fm only pay attention to a unique influencer, Im, which is the star for this community in some sense. Okay? So I have this collection, and of course I may have influencer who receive nothing. Okay? And so what are the conditions for equilibrium? Here, it is one I call internal stability. which means that the level of the contribution of IM is, and in that case, there is an equilibrium. It's very easy in a star. When there is a unique influencer, there is an equilibrium. Very easy to compute. Okay, so it must be this level, easy. But the second condition is external stability, which is no follower would like to follow another influencer. So all the other influencers of somebody in FM have a lower contribution. Okay? And so one can show that there is an equilibrium when delta is small enough. So this means that this is also a proof that for delta small enough, there is a Nash equilibrium. Okay? And actually, it can be, the condition is very easy. Basically, it says that the number of followers that an influencer has is bounded. I mean, there is delta, or the ratio, if you consider an influencer together with all his influencer, I mean, the spillover condition is satisfied for this group, okay? And the proof is, so it's easy to check. And the condition, I mean, the proof is constructive. And I can compute a particular equilibrium, which is generically unique, which I call hierarchical. Okay? It's very easy. For example, if you have homogeneous characteristics, this idea is very simple. Take an influencer who has a more numerous number of followers. Okay? With homogeneous characteristics, this means that her contribution will be the largest one when you form a star, because she has a more numerous number of followers, if characteristics are homogeneous. Okay? And you take this group away, and you continue with the remaining networks, and then until you repeat. And then one can show that it is an equilibrium, and it is a star's equilibrium. So, of course, at the end, you may have leftover influencer who receive no attention. Okay? So, here it's not very interesting, but it's just E3 has 2 followers, so with homogeneous characteristic. If you consider, for example, E1, he has only 1 follower. So if you form this pair, I mean, the contribution of E1 will be surely smaller than the contribution of E3 with all his followers. Okay? So at the first step, you pick E3 and the follower of E3, and that's it. You have now, it's finished. And I1 and I2 are left alone. Okay? So one can characterize all equilibria similarly by this decomposing the attention network. And in each component, you must have internal stability, an equilibrium within the isolated component, and external stability. Nobody wants to choose another group. Okay? So what are the causes of the multiplicity of equilibria? It's really due to the cost of attention, because of the cost of attention, follower may pay 0 attention to some of their influencers. Okay? This is really because you have this quadratic cost. Okay? And actually this is observed. Some people have quite many influencers, but they don't pay attention at all. And so you have this cost of attention, which means that you may not pay attention to some of your influencers. And you have also increasing returns for a group of followers when they pay attention to a smaller number of influencers, provided that when you reduce this subset of influencer, each follower has still an influencer in this subset. And this is why you have these increasing returns, but it depends on the networks, okay? Because you cannot always decrease your number of influencers if you want to keep an influencer for each follower, okay? So this is why to find all equilibria, I mean, I don't know how you can necessarily find all of them because it really depends on the network, okay? And so, I mean, this increasing returns for group, when in a group you have many followers per influencer, is why you have this rich get richer phenomena, okay? And what is interesting, I think, is that you can compare the equilibria. And so I will just speak on the first point. And if you have two equilibria, and I'd say that A is more focused on A prime, sorry, if whenever F pays attention to J at A, it pays attention to A prime at J. Okay? So this means that the subset of influencer to which F pays attention at A is a subset of those to which he pays attention to J prime. I am not talking about the level. The levels may not be ordered. It's just to whom you pay attention. So, of course, in a full support equilibrium is a less focused equilibrium, okay? Because you pay attention to all your influencers, okay? So if I have two equilibria that I can compare and with this focus, and if characteristics are homogeneous, then attention totals for followers, the contributions for influencer, the payoff for followers and influencer, they are more dispersed but have a higher mean at the more focused equilibrium. So in particular, if you have a full support equilibrium, which is the less focused, this means at the full support equilibrium, everything is less dispersed, but have a lower mean. Okay? And this is roughly true for when you have no homogeneous characteristic, if delta is large enough, so spillover are large enough. And this is now due to the convexity of the spillover. Okay? When you split a set into two subsets, you increase in some sense inequality, but you increase the mean due to the convexity of the spillover. At least the proof is based on that. So just a consequence, if you have, for example, a platform that seeks to maximize aggregate participation, which is the case when they are paid by ads, say they want, it's clearly the case, they prefer the more focused equilibria. For example, the stars equilibria, which are more focused than some other, okay? And if it's that you have a designer, I don't know, in other context, who would like to equalize the participation. Actually, I was at a conference with people from Facebook. They say we want to equalize. I don't know whether it's true, but they don't want to have stars. And a designer who would like to have equal participation as much as possible, then they prefer equilibrium with less focus of attention, okay? And so there is this trade-off between average participation and the dispersion of participation. So I have 5 minutes, okay. Oh, Sorry for you. I mean, I'm still... so this one, I mean, the stars equilibrium are stable with respect to local participation. Maybe this one is more interesting, is that an equilibrium is coalition-proof Nash equilibrium if and only if it is hierarchical. Okay, it's not strongly a strong Nash equilibrium. You can have deviation by coalitions, but not in this sense. So basically, this result tend to point to star equilibria, at least if you you agree with inequality. I mean, okay, undedicated, I will skip the formula, but just so each F chooses a single generation attention level, so and payoffs are quadratic. So this means that all best response are linear and increasing. So you have complementarities, and the analysis is very similar to the paper I was referring to before. Of Ballester, Calvo, Mengel, and Zenu. So it's not very interesting from technical point of view, but what to contrast, it means that now you have a single attention level, which is positive, and so this means that you have no longer cut in your attention. And this means that there is a single spillover measure, because I mean all the effects spread over the network, and it results in a single spillover measure, which depends, and people who know this type of study, which depends on some eigenvalue, dominant eigenvalue. I don't want you to dominant eigenvalue. Here, what is a little specific is that it's a dominant eigenvalue of some matrices, which are made with the matrix of the network. But I just want to say that these matrices are known as projection, and in a two-mode network. So I skip, I don't want you to read that. It means that a projection, you have this network between followers and influencers, and you derive a network between followers thanks to the indirect connection, okay? And this type of, so this means that you can derive how indirectly the followers are connected. And this type of tools has been used when on one side, say you have actors, on the other side you have movies, okay? They are not people, but you know the network, which actors plays in which movies. And you derive a network between actors, okay? Which means that there is a link between two actors if they played in the same movie, and you can even weight the link by the number of movies to which they participate. And then you can analyze the networks of actors with the projection. You lose a little bit of information, but it has been a tool that has been used. Okay? So I just, so since the equilibrium is unique, this means that you can study some recommendations, some design problems. So for example, you can, what is called targeting, where you want to increase a characteristic of user, the recommendation system, when you want to recommend some users to other, or the promotion of posts. And there have been many experiences. Because Twitter, I mentioned before, has been very useful, but there has been one, I like this one, because it was reported in The Guardian, and it was Instagram, which wanted to change and to promote some new post, actually video. And apparently they wanted to be like TikTok. Don't ask me too much about that. But, and actually the users of Instagram were very upset. And finally, Instagram had to withdraw, I mean, the new setting. So it was in 2022, so maybe it is not... so, I mean, you had just, you know, a network between friends, and they wanted just to send you posts of people you don't know, okay? And so, I mean, this type of strategy are quite common and are not necessarily successful. This is why it might be interesting to study. Of course, what would be interesting would have more detail. And now, I mean, empirics, and now, unfortunately, now, for example, Twitter was very open, but now X is not open at all. You have no data. Facebook, they don't publish their research, and so on. So it's quite, the reference now are quite old. It's difficult to know exactly what is going on. And so basically what I wanted to say, duality affects analysis, and dedicated attention leads to an endogenous formation of pairs of communication. And standard indices are valid only with undedicated attention, but actually the fundamental, I think more fundamental reason is that with dedicated attention, you have linear best responses. And the linearity leads to this use of these indices. It's true more generally, not only with duality, with a single action. It's also true, actually. That's it.
We have time for one or two questions. You know, we will push the next speaker a little bit. That's no problem. No? I have one. I mean, you know, when you speak about this network formation, and so I was thinking of the Brest paradox in transportation network. Namely, do you have the same kind of phenomenon where you start with a bipartite graph and there is a certain equilibrium with a certain amount of attention that's spent from the followers to the influencer, and then you add some connections, and all of a sudden the flow of attention in the equilibrium decreases as opposed to what you expect.
I don't think I have heard it, but my guess is no.
That's not possible.
I don't think that's
Okay.
true.
Okay.
But maybe,
Yeah. Okay.
I don't.
Okay. Thank you. Nothing else. So thank you again, Gabrielle.
Good morning to everyone. A quick announcement. Due to some last-minute cancellations, we had to make some slight changes in the program. We have updated the website, and we have the printed, updated program here in the hallway. Yes, exactly. Thank you.
You updated the program for this afternoon?
For this afternoon, it's only the regular session that switched, but it's mostly tomorrow.
Okay. We will check that. Yes.
Do you need a hand?
Can you? So one more lecture on fair division, number 3. When I started to be interested in, you know, the normative aspects of microeconomics, reading on social choice and so forth, I thought of the stuff that was done, the work on cake cutting, which was done by these mathematicians in the late 40s, I mean, after the World War II, was kind of an interesting curiosum, you know, something they did, but not really connected to what Amartya Sen and others and, you know, Waymark and so forth were doing on social choice. And then, since then, my view have completely changed. I mean, in the sense that, first of all, as I think I will show now, this work on cake cutting is really as basic and as fundamental as the sort of the other models I was describing before in those two lectures. And also, you know, another contribution which was very interesting by the computer scientists at the beginning of this century was to, in some sense, merge the considerations of social choice theory and those of fair division in a pool of axioms and considerations which now essentially are the same background. So I don't have time to elaborate on that. We can discuss it offline. But I do consider now that, you know, social choice, like the talk you will have to endure this afternoon if you stay in this room at the time where I speak, which is a purely social choicey talk. But in fact, you know, it's the same people, so you can expect the same sort of inputs and so forth. Cake cutting. Okay. So now the first statement is why cake cutting is really much more general. It's not a curiosum. It's not a particular thing about cutting a cake. It's actually a much deeper and more difficult model to handle. What do you have? You have a set omega, which is a set compact connected in an Euclidean space. In fact, in most applications, not application, but in most theorems, we are happy to deal with omega equal an interval 0, 1, because most of the difficult questions you can ask there, but potentially it is a compact set in some Euclidean space, and the shares, which is what we receive individually, are measurable subsets of this omega, right? So their set is the set of Borelians in omega, okay? And an allocation is a partition, right? So what will be the key here throughout is the non-atomic character of the cake, and in fact here indirectly of the utilities. I mean, what we want is to preserve divisibility, because we know that as soon as we introduce indivisibilities, which here would correspond to atoms, then all the analysis, I mean, a lot of new difficulties appear. So we maintain this divisibility by dealing with a non-atomic set of that we divide, and by utilities which are non-atomic, which means that the smaller pieces of the cake necessarily affect less and less your utility, right? I mean, it's the obvious interpretation of non-atomicity. So, yeah, examples, yeah, you divide a cake, you divide a piece of land, you divide a road in time slots, but, and that's the second line, you are also encompassing everything we have done so far. Because think of an Arrow-Debreu standard thing with three goods and agents who have their Arrow-Debreu preferences over these three goods. How do I embed that as a special case of cake cutting? I make the cake to be an interval 0, 1. I divide it in 3 intervals. I call the first interval good A, second good B, third good C. An allocation is a partition. What an agent receives is a little bit of the subinterval A, some other amount of the B, some of the C. My utility depends on the combination of how big is my share of A. You see that everything fits. It's a general utility over shares of the cake, and it has discontinuity properties. So yes, we are in a more general model, just because we have preserved this divisibility. Okay. So therefore, of course, it will be harder to get general results. I mean, don't expect that I will end up with a golden rule that is that we are very proud to advertise and recommend in all contexts. Okay, so let's start with what those excellent and famous mathematicians did. It's not just Steinhaus, but never mind, which is the additive cake. What they were looking at first were cake division and their immediate, because these guys, I mean, were very deep on probability and so forth, so their immediate modeling idea was my utility over the cake is a non-negative additive measure, right? Okay, so it's the equivalent, if you transport that in the example of Aldebreu and so forth, it's the equivalent of linear utilities, right? So each utility is a positive non-atomic measure, UI, on that set, okay? And now, what were they discussing? They didn't call it like that, of course, but what they were discussing was the fair share. No more, no less, which is, in my view, I mean, something more fundamental because more simple and of broader application than the envy-freeness. I mean, envy-freeness also plays a role in this model, of course, but what I mean is that fair share, transcends by a lot the context of fair division of private commodities. So anyway, in this context, with an additive cake, with a cake on which utilities are additive, your fair share as agent I, if everybody is like you, if everybody shares, you have n people and they all share your utility, and now we want to divide the cake, then it turns out that the best share that you can guarantee to everyone is 1/n of the utility for the whole cake, which is similar, it sounds a bit similar to, in Aldebreu, UI of omega over n. Here it's a bit different. And the proof is not trivial. But it's a simple consequence of the Lyapunov theorem. The Lyapunov theorem in probability, one of the Lyapunov theorems, is the fact that if you have an additive measure which is vector valued, so you have a U1, UN, a vector of measures, and then you look at the image that they have over partitions, and that set is a convex set in the set of utility profiles. Which means that in the cake division problem, one feasible outcome in terms of utility profile is 1, 0, 0, 0, 0 when you give all the cake to agent 1, as well as another is 0, 1, 0, 0, 0 when you give all the cake to agent 2, etc. And by the convexity of this image, giving 1/n of the cake to everybody is feasible. All right? And it's also clear that you cannot do more. You cannot guarantee more to anybody. So therefore, this is the best and unique and undisputable fair share that you should enforce. All right. So good. And now what do they do? Yeah, I will start before telling you what these guys did, which is of course they did a bit more than that. But let me jump immediately to a very recent result and very remarkable, which is that at least in this additive case, in the case of additive measures, things are actually working very well, very much like in the Aldebreu case, but much more general, because we will actually go back to the competitive equilibrium with equal income. Remember, everything is positive. I'm not talking about bad, but so I have the context, the concept of envy-freeness, exactly the same as before. I have a notion of competitive equilibrium because now the price P is an additive non-atomic measure on B, on omega. And given this problem where U1, UN are all non-atomic measures, unit measure, or not unique, unit, that doesn't matter. And now we look for a partition maximizing the product of utilities over the set, right? Over all feasible partition. And it is, and we find that it is a competitive equilibrium with equal income. I'm not sure, I don't remember, but I think you don't really have the converse is difficult. The converse is difficult, and, you know, I don't think it's, well, but anyway, this is already very nice. I mean, the corresponding price is unique, and so is the welfare profile, okay? So, moreover, I mean, you know, in fact, resource and population monotonicity, you can have that too, and so forth. So that's great. That's great. But now, is it useful? Is a different matter, because I mean, if you think of applying that to a model where your omega set is really a multi-dimensional convex compact, and then you have measures which are a bit complicated. The difficulty of identifying exactly what happens is computationally non-trivial. And so that's one thing, but I'm sure these guys, because Segal Alevis, they are computer scientists initially, I'm sure they can say, they can do something nice. More importantly, there is the issue that for yourself as an agent, even if your utility indeed sounds like it is additive, to formulate it, to give to the designer, okay, here is my measure over the whole set, that's a difficult proposition, right? And that's why, in fact, that's a motivation for what the mathematicians did, which was to try to think about these concepts, especially the fair share, in a way which is more practical, which is a mechanism to implement it, okay? So they were concerned by this concern, fair share, and then later, when this tradition continued, there was the same concern with envy-freeness. How can we implement things like fair share by simply asking agents to play simple mechanisms? So it's in a sense, it's an implementation problem like this. I mean, we will look for simple mechanism, but to implement the fair share, that's what those initial mathematicians did, and implement envy-freeness, that's what people did after, continuing on the tradition. But this implementation will be in a very specific sense. It will not be, you know, a la Maskin, you know, some beautiful mechanism of which all the equilibria of a certain type capture exactly what you want. No, it will be much more limited than that. It will be the worst case guarantee meaning. Namely, these mechanisms will give every participant a simple way to play, which will, for instance, in the case of fair share, which will guarantee in the end that the share they receive is at least the fair share, irrespective of how the other agents are behaving in the mechanism. Without paying any attention to what they do, you know that if you play in the proper way, which we will call, if you want, the prudent way or the sincere way, you do what the mechanism tells you to do, then you are sure to get the fair share. Okay, and that's the only thing you do, but that's already not bad. Okay, it's not too difficult to implement the fair share, and in fact, I think by reading this, first of all, many of you will have encountered these things before, but if you have not, you know, it will be very intuitive. I can at least list 4 different 4 different mechanisms. Diminishing share. What's diminishing share? That's the one, the original one. You order your agents in some priority, arbitrary. The first agent cuts a share of the cake, which he proposes as a share for herself, him or herself, right? The second agent has the right to take that share upon taking away a little piece from it. That piece could be very, very small, so essentially he has the right to take it out. You have the right to take a slightly smaller share by taking away a little bit and saying, that's good enough for me. Third agent can do the same, take away a little bit. That's good enough for me. And at some point, nobody touches the share anymore. At that point, the last person who touched the share gets it. So you see, and then once some person has taken this share, this initial share, you start over with the leftover agent and the cake. So you see that your strategy is very simple as long as the share proposed are above your fair share. You trim them a bit to the level of your fair share, and you say, I propose that. If the share proposed by the first agent is less for you than your fair share, you don't touch it. So you see that in that case, since eventually the share that is given away is less than average, is worth less than average for you, in the cake that remains, your average fair share divided now by n-1 will actually be bigger. So that's why you are safe. That's why you have this guarantee. I mean, if you don't... so in a sense, the good thing here is you only reveal, you only have to not reveal is not the good term, but you only have to conceptualize what do you think is a fair share. So, which I think, you know, cognitively is very realistic. Yes? Yes, the moving knife is... Yes, moving knife, but moving knife is fundamentally different because in the moving knife, it's the designer, the mechanism designer who takes the initiative. And the first one is taken by the agent, which in a sense is better because the agents know better what is a good part of the cake. In the moving knife, what happens is you take the cake at one extreme, you put the knife, and you start moving it. That is, you cut successively increasing, an increasing share, and people in the participants can say stop whenever they are happy with the cake, with the share that you have cut until then. Okay, there is no problem with the division of the tie breaking. And of course, your strategy is as long as the share which is proposed is less than your fair share, you don't move. When it reaches your fair share, you stop immediately. Because if you don't stop immediately, you take the risk that someone will stop a bit after you, but before you can move. And therefore, now the cake that will be left after in the next round will have on average a worse fair share for you and so forth. So it's same idea, but the first one is probably more interesting. Okay, so then same thing, ascending ocean with an exogenous, that's essentially the moving knife where you say, oh, okay, I have a measure which is a benchmark measure that is exogenous to the agent, and I raise a number which says, and if you accept, if you say I take, then you are entitled to take a subset of size X, if this was X as measured by mu. Same sort of idea. The last one is the one we will look at later, which is a generalization of divide and choose. So we will deal with that one later because it's one with interesting applications. Okay, So good for fair share. We have something nice and simple. What about envy-free? So it's very well known. You know, this is probably the one mechanism design that goes back in history very far. I mean, when I teach on fair division, when I teach on mechanism design, I always take two examples. You know, divide and choose that you find in the Bible, you find in Greek literature, and then the other is plurality voting. Because I always think of these Germanic tribes, you know, who choose their leaders by asking, you know, by having people form groups, and then the group who is proposing a certain leader puts him on a shield like this, and then people are around, and then you measure how big are the group, and the biggest group, well, that's the guy who is elected. I mean, and that's the way you read in history that they were doing. So that's a sort of a very early voting story. Okay. All right. So it's easy to do plurality voting with n agents. It's not easy to do divide and choose with more than 2 agents. For instance, there is those two mathematicians, Selfridge and Conway, propose a way to do it for 3 agents. And it's about the best way, that is the simplest way that is known. And remember, this is a method for people endowed with additive measures. The additive character of the measure here is crucial. Okay, so it will happen with the agents. We will end up with an envy-free allocation by a succession of cuts and choices made by the agents themselves. So you have an arbitrary order of the agents, 1, 2, 3, that's totally arbitrary. And the first agent cuts the cake in 3 equal shares. By equal share, I mean equal share for himself, right? It's his problem if he decides not that the shares are not equal, it's fine, but then he cannot guarantee anymore that in the end he will have an envy-free, he will not have envy of the others. So again, when I say equal shares, I'm describing the prudent, safe strategy. Okay, then agent 2 is supposed to take away a piece of her best share. This trim could be 0, but in general it's not, to make her best share, which we will say is A without loss, to make her indifferent between A and the, to make her indifferent between the A star is the trimmed share after you take away a little bit, and her second best share. And so what agent 2 has to do here, which is the non-trivial part, is agent 2 sees A, B, C. Okay, let's say that agent 2 prefers A to B to C. She's supposed to trim A so that the trimmed part A is A star, is indifferent, is worth the same for her as B, her second choice. Okay. Okay, you need to tell me that story later. I don't know it. No. You are not allowed to make them equal. No, you are not allowed to do that. Trimming is like putting aside a tiny glass with a little bit of wine that we will share later. The trimming is, there is really a thing here. The trimming is put aside, just like in your cooking recipe. Put those trimmings aside, and then, no, you really put them aside. That's the way where the mechanism is smart. I mean, you put aside and you deal with it later. Okay, so now we have A star B, C, and the agents will pick a share in the order 3, 2, 1. Okay, that's important. It's 1 and 2 have been identified. The last one start, then 2, then 1. So you see that at this time there is no envy because player 3 took the best share among A star, B, C. So he's not envious. Player 2 still had A star and A as equal first best among A star, B, C. So player 2 gets one of those two and has no envy. And player 1 has no envy because the shares were equal to start with. So all the shares are worse, and he's not envious. He's not even envious of A star, which is worse. Okay? One important qualification is that agent 2 must pick A star if 3 did not, because we want to avoid that agent 1 ends up with A star. Okay? All right. So you see that it's already a little bit subtle, right? And then you have allocated everything unless except the trimmings. Now you will allocate the trimmings in an envy-free way, and because of the additive character of the measures, envy-freeness will be additive. If I have two cuttings of two different parts of the cake and they are envy-free each time, then you are envy-free globally. I mean, that is additive here. And the trimming, for the trimming, you have to now distinguish, you have to now identify who is the agent who got A star. So you call that among 2 or 3, because remember, A star has to be taken by either 2 or 3. So then if I is the agent who did not get A star and J is the one who got it, and then it is agent I who cuts T in 3 equal shares, agent J then picks a share of the trimmings, then 1, then I. So at this level, you need to do the computation to check that it works. But you see, it's nice. I mean, you can, if you don't have access to the slide, you look, it's everywhere. You will find the description of this very nice mechanism, right? But still non-trivial. I mean, you need a little bit of, being careful. Okay, so it was took a long time. Selfridge Conway, I think, is in the early 60s or something like that. Took a long time to try to generalize this procedure to any number of agents. It was a very nice open problem. The first to find something were Brahms and Taylor, 1995, with the difficulty that their mechanism had no finite bounded size. You could not tell in advance, this is how many times you're going to have to cut and choose, because the thing was using pieces of trimmings that would be smaller and smaller. So now it became really crumbs that you were generating. And then Aziz and Mackenzie, computer scientists, found a way to improve the mechanism so that you could indeed bound the number of cuts, but it's an obscene number. It's some power of power of power. So essentially, this is to say, it just doesn't work to try to extend, because you end up doing many, many cuts and generating many, many crumbs, and, you lose the contact with reality. But still, still there is something, because in any case, at least 3% problems, do make sense. So, okay. All right, non-atomic cake. So let's try now. When I say non-atomic cake, is by opposition to additive cake. In other words, now I want more general preferences, right? Because additivity is very peculiar, and on top of this, we have some strong results for additivity. So let's try to see. So I will use the Lebesgue measure. You need to have some proper definition of continuity of your utilities. So one way to do it is to take the pseudo matrix, which is the symmetric difference of shares, and then you call a utility function over shares continuous if it is continuous over the set of Borels with this symmetric difference. Okay. I'm sure there are other, the results do not depend on that. Okay. At this level, let's not have any monotonicity assumption. So let's try to be really general to also include the possibility of bad parts of the cake. So the thing we have to divide may include parts which you do not want, because if you add them to your share, it makes it less valuable. So we really maximize the generality. Okay. Even in that case, it is indeed possible to show, and it's a nice clean result, that envy-free partitions exist if you restrict to good cakes, in which, but good cakes in a fairly limited sense. It's all prefer any share of positive measure to nothing, right? Or vice versa, meaning all prefer nothing to any positive share, meaning that it's all bad. So it's a cake in which I cannot give you a share and you are unhappy. But it's not true that a bigger share makes you more happy. See what I mean? The only thing we want is to have a zero level of utility. I mean, if I don't give you anything, that's your worst outcome. You want some part of the cake, or vice versa if it's the same for everybody. And then the existence of an envy-free partition is guaranteed, and it's essentially a fairly simple version of the KKM, one of the KKM theorem. I mean, the one about you look at the subsets of partitions where agent 1 is a non-envious, and then you say, okay, no, sorry, the set of partitions where agent 1 is envious of everybody, and that, right, just envious, and that contains the face of the simplex of the distribution of 0, 1, because we are distributing really the interval 0, 1, where you get 0. I mean, it's a simple proof. I mean, it's not important to, but it's a simple proof applying a powerful theorem, right? What's nice about the result of Su in 1999 is that he goes beyond the simple model with private property shares. He applies the Sperner lemma in the same model, but in addition to caring for your share, you also care about the distribution of shares among others. Your utility is defined not over just your share, but over partitions. And again, you only have the thing that you all prefer any partition to a partition where you get 0. Okay? So that's neat, and that requires, again, those are nice theoretical results. I mean, they show us that envy-freeness is not out of reach, but they don't tell us anything about Pareto optimality. Oh, sorry. Yeah, it's the same. It's the same. You take this. You go in the shoes of the second person who receives that share. Right, and you are, it's the same. But again, no connection with Pareto optimality, which is a big problem. I mean, when you have fair share, when you guarantee a minimal level fair share, then automatically you guarantee that you can be Pareto optimal and satisfy the lower bound, right? Because you just go up in the utility space until you hit the Pareto frontier. But here you don't have this connection with Pareto optimality. In fact, I don't know of any really general results which deal with this kind of issue. It's one of the big open issues. You see? When are NV3 and Pareto optimality compatible? Does an EF division exist where some shares are worse and some shares are better than nothing? In other words, can we remove the assumption in the theorem I explained before, which is that getting nothing is always the worst? You could go to the level where getting nothing is getting nothing, but there are some shares which are worse, and there are for you, and there are some shares which are better. So you fully eliminate any monotonicity assumption, okay? And those reach a level of difficulties which, as you will see, become mathematically very, very high. Okay, and then another one is find at least one maximal fair share. We will discuss fair share in that general context. Right now, I have not given any fair share for you to think about, but we will propose one, but one that we know is not maximal in the sense that there are ways to guarantee more, but we don't know exactly how. You will see the problem. Okay, so let's do that now. I stop with no NV. I mean, because if no NV and Pareto optimality we don't know, well, I mean that's the first stumbling block to get rid of. I mean, maybe they are incompatible, and then we have to restrict attention to models when they are compatible. But, okay, so fair share. So remember, of course, now we are not talking about 1/n of your utility for the whole cake. That makes no sense. I mean, we don't have even monotonicity and so forth. So let's go back to the initial definition. The fair share will be a function fs which associates to every utility a number, a level of utility, such that for any profile U1, UN, there must exist a partition in which everyone achieves at least that fair share of his or her own utility. And now come, the important notions which are in the spirit of divide and choose and will play a role also in the next lecture. The unanimity test, which is, remember, it's the fact that if I look at the fair share property and I say, suppose that everyone is like me, then in particular, this function fs must satisfy that the level fs of ui can be guaranteed to everybody in a profile where everybody is like me, in a unanimous profile where everybody is like me. And because of that, it must be that a fair share of ui is bounded above by the so-called max-mean ui, which is the maximum over partitions of omega in n shares, such maximum over partition of the worst share I could get, right? Because if the argument is like this, give me the profile UI for everybody, find a partition where everybody gets the level fs of ui. This is a partition here, and therefore someone must get at most minimum of ui of si in this partition, and this someone could be me. If you guarantee it to everybody, everybody has to get it, so that's it. I mean, that's in an immediate consequence, right? So, okay, all right. That's interesting. That's a concept, this concept of max-mean plays a role also next time. I mean, okay, tomorrow, if we are still there tomorrow, yeah. max min certainly is too much. It's too much to ask for max min, because preferences can have can be orthogonal to each other in the following sense. I mean, think of omega as being the planar circle, not the disk, and just the circumference. And then you have agent 1 who gets a utility of 1 for the share if and only if the share contains either the north semicircle or the south semicircle. So any share where there is either the north or the south, the utility is 1. Any other share, 0. Okay? And similarly, for agent 2, to get a utility of 1, his share must contain either the half circle from 0 to 6 p.m. or the half circle from 6 p.m. to midnight. So it's clear that the max min of any of those players is obtained by taking the partition in the two half circle, which gives him each utility of 1. So therefore, the max min of U1 is 1. The max min of U2 is 1. And together, they cannot both have, because these two partitions are not compatible. So it's a trivial observation, but important because it shows the, okay. So, all right. Okay. So, max min is not good. So let's see if max min is not good, why not try min max? Okay. And min max will actually end up working with some qualification. What's the min max? Now it's the mean over all partitions of the best possible share I could get in this partition. So in the max min, I am the divider. The max min is where I am potentially the divider of the cake into shares, and then I cannot control which share I get. Now in the min max, it's the opposite. I am a chooser, but I'm the favorite chooser, the priority chooser, so someone will cut into a bunch of share, and I will have first choice. So in a sense, it may be good. It may be good. Min max utility of the best share in the worst partition of omega. So at priori, it's not completely clear which one is best. Notice that if UI is additive, the min max and the max min, this minus is a typo, there is no minus in the max min, are both the classic fair share. Because if I'm the divider, of course, the safe way is I divide in equal shares. And if I am the chooser, the best chooser, out of n shares, one of them is worth at least 1 nth because utilities are additive. But in general, is there a relation, and also in this context, an envy-free partition will give you the, no, sorry. This note here is that in this general context, not just in additive case, if you have an envy-free partition, it will guarantee the min-max. Yes, because in an envy-free partition, I get a share which is at least as good as that of anybody else, right? So it's as if I have first choice in that particular partition. And the min-max is the worst utility I could get if I am in that position of being the first chooser. So the min-max is not is something that we feel will be, of course, often feasible, and that's the goal that we have in this particular theorem, which will be the end, with which I will finish explaining what's going on. So the min-max utility is a feasible guarantee in this model without without monotonicity assumption. So even if you don't have the assumption guaranteeing the existence of NV3, even if you have parts of the cake which are worse than getting nothing or better than getting nothing. So it is feasible. It is below the max mean always. Again, forget about this minus. The minus is a typo. It's just sorry about that's just ignore the minus. Sorry about that. So the min max is less than the max mean, and to implement the min max, we can apply a proper generalization of a divide and choose algorithm where Kuhn generalized in the 60s the divide and choose method in a way that I will show you, which is out of all the ways to give you, for instance, the fair share in the additive case is, I think, clearly the best, because here, in a fully general context, it allows you to divide and to implement a plausible fair share in a number of cuts which is not large, because polynomial. So how does the proof goes? The first one is, how do you prove min-max less than max-min? And for that, there is a really tough topological lemma, the equipartition lemma. So this has nothing to do with comparing your utility and the share of other people. It's more the following. If I give you one of these utilities, which are continuous in the sense explained, and on this problem, then it's possible for agent I to divide the cake in n shares which are equal for agent I. Okay, so cutting in equal shares is possible, right? So if utilities are always non-negative, it's clear that you can do that, because the existence of NV3 partition, if you have NV3 among a group of people who all have the same utility as you, that means you all have the same utility, that all the shares are equal to you. So that's fine. I mean, and remember that non-negative utilities, okay, so, all right. Now, it is still true in the full space. Remember that in the full space where there is absolutely no monotonicity assumption, the existence of NV3 partition is not guaranteed. That's another difficult theorem. But here, in order to get that equipartition lemma, we had to, I mean, Anna and I, we could not do it, but then we got in contact with, indirectly, with two mathematicians in Moscow, and using this advanced tool, they actually, in the end, that paper became a separate paper from ours, because that paper just proved the equipartition lemma, which is a natural thing, but a difficult one, but also potentially more general. So that's why it makes sense to. Okay, so given this equipartition lemma, this is what we do. This is what the Kuhn's procedure does. All right, we select the divider in successive step, of course, as usual, with an arbitrary ordering of the players. So the divider picks a partition, right. It's written later, but when the divider picks the initial partition, as usual, he takes an equipartition. He divides in shares which are equal from his point of view. There is no question there. And that's, of course, we already used the equipartition lemma. And every other agent reports one or more acceptable share, meaning acceptable, guaranteeing the min-max level. Since the min-max is the worst possible level of utility that you get if you get first choice, if I propose you any partition, one of the elements at least is better than your min-max, because that's the one you would choose if you are first chooser, right? So therefore, everybody else has some acceptable shares. Acceptable means above the min-max guarantee. So now, there is a little graph theoretical result, which is a simple application of Gala-Edmond decomposition, which says the following. Given that, you will see on the example, so given this proposed division and the fact that everybody else has pointed to at least one acceptable share, it is possible to find a number k, and I will take the largest, such that I can give to the divider one share and to k minus one other agents an acceptable share, and in such a way that each allocated share is unacceptable to those who are not, to the n minus k remaining agents which are not immediately served. In other words, what I do in that step, and I say the divider put these equal shares, so he accepts all those shares. Everybody gave me some acceptance. I can identify at least one and perhaps more agents such that I make them happy, I give them an acceptable share, and I make sure that the others, those whom I don't serve, they don't care for those shares which have been allocated because they are all unacceptable to them. And that's why later on they will not violate the min-max, because whatever has been given is in fact below what they accept, below the min-max. Okay? And then if you follow, if you are sincere, you don't try to play tricks, in the end you will guarantee min-max. Okay, so we have time for a quick example. Right, 5-agent example. So the divider 1 says A, B, shares, puts 5 shares, A, B, C, D, E. Agent 2 accepts one of them, A. 3 accepts A, B, and D. 4 accepts A and B, and 5 accepts B. So now the best I can do here, if I want to serve at least one agent plus the divider. The divider, it's easy to serve her because all the shares are good, so whatever you give to the divider, it satisfies the min-max. So you give to C, to the divider, the share C that nobody else likes, and you give D to agent 3 because D is only acceptable to 3, and similarly C is not acceptable to 2, 4, and 5. So once you have given to to 1 the share C and to 3 the share D, then the remaining agent 2, 4, 5 do not care for the 2 shares which have been distributed. Okay, and then in the second round, and you have 2, 4, 5. So now 2 gets a division of whatever is left, which is not left, of course, as separate share, which is put together now as a big share, the union of the shares A, B, and E. And then the divider do 2 split in 3 shares, because there are 3 left, F, G, H. Then in parentheses, there is C union D. These are the 2 shares that we had before. Then here it happens that 4 and 5 both like G. So we can only do the trick of before by giving a share to agent 2, one of the 2 left over. So let's say we give F to 2. And then now we are left with 4. Who becomes the divider to divide what is left after agent 2 gets F's, which is G union H. And then boom, then that's a standard divide and choose. And the trick that guarantees that you have the min max is that if you look at this level for what you give to 4, at this level, if 4 in his mind think of the partition F, G, H, and then C union D, which have been done before, then those two are unacceptable. And therefore, among the three, there must be one which is acceptable vis-à-vis the initial cake. Because in the initial cake, for any partition of the whole cake, at least one share is above the min-max. And it cannot be either C or D because they have been excluded by these agents 4 and 5 and 2, okay? So you maintain that property of min-max, and therefore you are sure that in the end you get your min-max, okay? So that's the thing. That's the thing. So that's where I stop because, you know, in a sense, this is all we know in the fully general model of cake cutting. I mean, there is, for instance, this powerful algebraic geometers, they discuss, you know, context in which NV-free shares exist, even if you have zero monotonicity assumption on preferences. They have results where it turns out that the fact that the number of agents is a prime number helps to get existence of NV-freeness. Don't ask me to give anything more than a couple of references to where you can read the paper, and good luck, because you know it's very tough entry cost in that literature. So maybe, you know, maybe we can hope. My hope is that we may find ways to simplify a bit the general model, to find a rich class of applications, because to be fair, I mean, you know, there are not too many sort of concrete applications of this problem with you know, a cake which has some kind of geographic or other representation, but the mathematics is very rich. I mean, so okay, thank you. So. Okay. Any questions? Oh yes, Joel.
Can you comment on the extent to which these things are constructive or algorithmic? So I'll be a little bit more specific. So in the Steinhaus theorem, you could imagine somebody waving a knife over the cake. In Kuhn's algorithm, it sounds constructive, but presumably the equal partition lemma is not constructive at all. So that what Kuhn's person does is the result of something that's hard to explain here. So
Yeah.
is there a sense in which you can identify how many of these things somebody can do?
Yeah. I certainly for the equipartition lemma, I mean, I don't think it is constructive. Maybe.
I've been trying to understand.
Yes.
But it's better if we engage. I mean, this especially once you understand, and I cannot like the top mathematicians already try.
Yeah. Oops.
So that proved to me that it's not constructive.
Yes. Now at this point it is not, no. And we would need some more specification of the model. Yes. Yeah. Okay, thank you.
Stony Brook, I think there was no longer a conference in Columbus, okay? And it's still now in Stony Brook. So I think you know that Sergiu has been working a lot with Andreu Mascolel, and with computer scientists and alone, and with Foster. I think he's your co-author now. Okay, next time. Okay. So I think I leave you the floor because just it's more interesting what you have to say.
Thank you. Okay, now let's see if I can master the technology of holding this and speaking. You know, I need my hands. How can one speak? Okay. So since there are students here, I decided to start from scratch, to start very basic, okay? So some of you may have heard some parts of this talk. I can guarantee to you that no one has heard everything because there is some new stuff here, which I haven't yet presented. So there is something for everybody. Okay, so we are going to talk, joint work with Dean Foster. And there are papers. This presentation and all the papers are on my website. You are welcome to browse and see. You can click on any of those. Okay. Calibration. Okay. So I usually start my talks on calibration with a story. When I was a kid, before everybody, almost everybody in this room was born, or even, there was one profession that everybody ridiculed: weather forecasting. There were cartoons showing the weather forecasting saying tomorrow is going to be sun and he's in a bathing suit and torrential rain, okay? Or the opposite, okay? Anyone seen cartoons on weather forecasting lately? No. Why? Well, they are much better now in forecasting. That's one answer. But there is another answer. Forecasters don't say tomorrow there will be rain. They say the chance of rain tomorrow is 70%. And it doesn't rain. Well, I only said 70%. I didn't say for sure. What do you want? Okay? Nobody now ridicules weather forecasters, right? Problem solved. Well, problem solved, but why does he say 70%? He could just say 50% every day and it will solve the problem. Does this 70% have any meaning? Okay? In fact, that's a beautiful question. I remember a few decades ago, even at the center, that there was a discussion of what exactly does this mean, how do you interpret, and so how do you interpret this 70%? Does it have any content? And in fact, the answer is trivial. Ex post, as usual. Yes, after you think about it, oh yes, that's clear. 70%, what's probability? Probability, we think of it, if we repeat an experiment, in the long run, that's a fraction of times that this happens. In the limit, roughly, okay? So when the weather forecaster says 70%, what should we check? We should check how often there is rain. Okay, I just said rain. No, nothing else. No, we are not yet at thunderbolts. Okay, okay. So we have to check how often there is rain among the days when he said 70%. And that should be 70% more or less. Okay, so when the forecaster says the probability of rain tomorrow is P, then we are going to say that it's calibrated if for every 70% that he's going to use, the frequency of rain in the days when the forecast was P is P, or close to P, okay, in the long run. Okay, that's calibration. Okay, now, when you require this, now that's not so easy to be calibrated, okay? But now you can see I have nothing in my sleeves, right? Theorem. I can provide calibrated forecasts. Not in Brazil, okay? Any place in the world you would put me, okay? In fact, even against a rainmaker who is an adversarial rainmaker, so rain is going to be decided by an adversary, as in computer science adversary, which is someone whose only aim in life is to make me as a forecaster look bad, Okay, doesn't care about crops or something like that. Okay, so here is the theorem. Calibration can be guaranteed no matter what the weather will be. Okay, and that's a beautiful theorem due to Foster and Vora. In fact, Dean Foster tells me they couldn't publish the paper. They sent it to journals. At that time, I think they would still send hard copies. And they, after a few weeks, they'll get a desk rejection saying, this result cannot be true. You have not assumed anything. Okay? No, not that we found a proof, no, but you are making a claim that is impossible. They got desk rejection after desk rejection. Finally, it was published in '98, I think in Biometrica, in a good journal, yes, but nobody believed that result, okay? In fact, there's a beautiful, and there is a very simple proof of that result. Yes, when Dean Foster was in Jerusalem and gave a talk on this, and in the break I said, Dean, I have a proof for you, okay? And I'll give you the proof, okay? The proof is very simple. So let's discretize the problem, take finite horizon and finitely many possible forecasts. That it doesn't matter, that's only epsilons. Think of the game between the forecaster and the rainmaker. I want to show that no matter what the rainmaker does, the forecaster can get calibration. Okay, let's apply the minimax theorem. Assume that I'm given a strategy of the rainmaker. Given a strategy of the rainmaker, which may well be a mixed strategy, that translates every day in a probability of rain. What's going to be my forecast? That probability, maybe rounded up to the grid. So it's trivial, almost trivial. Again, there are some technicalities, but conceptually it's trivial that if I know what the rainmaker does, what is the probability of rain every day, I can provide calibrated forecast, right? It's a complete triviality. The minimax theorem says you don't have to know anything. There is a strategy guaranteeing calibration no matter what the forecast, no matter what the rainmaker does. Amazing, right? In fact, for a few decades, I keep saying, find me a more striking use of the minimax theorem. There are many things that are proved using the minimax theorem. I find this the most striking one. I mean, again, if you know what the probability of rain is, of course you can provide calibrated forecast. Conclusion, you can guarantee calibrated forecast knowing nothing. Unbelievable, right? Well, find me a better use of the minimax theorem. That's a challenge, okay? Nobody has yet raised to it. Okay, what's bad about this proof? I can't only say good things about it. Yes, I have to say something bad. What's bad about it? It doesn't tell me how to construct calibrated forecast. It's an existence theorem. But there are ways to construct it. So there are other proofs, of course, and that's the work of Andreu. You just mentioned Andreu, right? So Andreu and myself, using black hole approachability, which is a beautiful tool. I'm not going to talk about this today. There is a simple procedure by Dean Foster, which is based on this approachability, but it simplifies it in a beautiful way. And then there is something even simpler. I think it's the simplest. I'll show you what it is, which is called forecast hedging. Okay? So what's forecast hedging? Okay? We call it forecast hedging. I'll explain to you why we call it forecast hedging. One reason, it has the right initials. Nobody understands that. Foster Hart. Foster Hart, that's FH. Yeah, that's why we call it forecast hedging. No, I'll tell you why we call it forecast hedging. Sorry, I have my... Okay, let's make a graph. Forecast horizontally, okay, and frequency of rain vertically. And assume I'm in some period. And let's... okay, so what's, first of all, perfect calibration? Perfect calibration means everything is on diagonal. When I said 50%, the frequency of rain was 50%. When I said 20%, frequency of rain was 20%. So perfect calibration means all the points will be on the diagonal. Okay? Now, let's, for simplicity, look only at, say, 5 possible forecasts, 6 possible forecasts, yes, 20% multiples, just for illustration, yes? And assume the black dots are the situation today. So today, I have to provide a forecast. What's my data? My data is like this. In all the days when I said 0%, there was, let's say, 90% frequency of rain. In the days when I said 20%, there was 60% frequency of rain. So those black dots are the graph that describe the history. For every forecast, the frequency of rain in the days of that forecast. And those dots are something. I have no idea what they are. Okay? What do I do? Here is the procedure. Okay? Find a dot above and a dot below. Who says I can find something like this? I say. Why? Well, because the first dot is above the diagonal, because 0, the frequency of rain in 0 must be greater or equal 0. The frequency of rain in forecast 1 must be less or equal 1. So first dot is above, last dot is below. What can we do? At some point we must cross the diagonal. Okay? So here's a crossing of the diagonal. Then what I would like to do is to use this forecast. This one. But I'm limited to using only those. So what do? It's not because of the limitations, because it's very important what I'm saying. I'm going to forecast C1 or C2 with probabilities P and 1 minus P that give me this in average. That's it. You do this every day. So now there will be rain, no rain. I am adapting this picture, which means one dot is going to change, because whatever forecast I used, either this dot or this dot will change, depending on what happened, and I keep doing it. No AI, okay? No heavy computing. This works. Can't be much simpler than that, right? Okay, now proving it is a little more subtle. It's not an entire triviality. It takes a little while. It's a beautiful exercise, by the way. Not easy. I mean, not immediate. It's not a one line. You need some computations, but it works. Okay? Now, we're all the time talking about forecasting. Okay? No, there is no forecasting here. It's what we call backcasting. Okay? Really what we are doing, I cannot forecast what the rainmaker is going to do tomorrow, because I said rainmaker is arbitrary. Okay? What I'm really doing, I'm looking at my track record. My track record is exactly the graph you saw. And what I'm doing, I'm improving. I want to make it closer to the diagonal. Okay? So that's really backcasting. Has nothing to do with forecasting, but to use it for forecasting. Okay? Yeah, by the way, I found a quote from a German philosopher. It's a prophet looking backwards. Yeah. Okay. Walter Benjamin, a historian, picked it up. Anyway, okay. Now, just for economists that like to see data, okay, here is some data. That's from 538 from the website. You know, that's Net Silver's website. And you can see calibration plots. That's exactly what you get, what it has there. And it's pretty much close to diagonal. You know, sports, politics, again, data, there is less data. It's not so bad. Okay, a few misses. Yeah. Here is another one, I don't know, election betting odds, whatever, okay? So forecasters are calibrated. I mean, look, if I can be calibrated with such a simple thing, why shouldn't they be, okay? But never mind. Okay, now, so that was the introduction on calibration, okay? Now, let's take an example, okay? Assume, just an example, this is an example, yes? I'm emphasizing, yes? That's not how reality is. Assume that we have an alternating sequence of rain, no rain, rain, no rain, okay? And here is my good forecaster, let's call him forecaster 1. For rainy days, he says 100% chance of rain, sunny days, 0% chance of rain. Can't be much better than that, right? Clearly calibrated, because when he said 100%, every day there was rain. When he said 0%, every day, when he said 0%, no rain. But here is another forecaster. He says 50% every day. Is he calibrated? Sure. Because on all the days when he said 50%, which are all days, the frequency of rain is 50%. Okay? So both forecasters are calibrated just as well. Okay? But we have a feeling that one is better than the other, or one is better than two. Okay? Calibration does not capture that. Okay? We need something else. Okay? So F1 and F2 both have calibration score 0. What is the difference? So let's think about forecasting as partitioning the days into bins. So the forecaster that says 100% and 0% partitions the days into the 100% bin and the 0% bin. The second forecaster just has one bin, 50%. All days go into the same bin. Now, when we look at the variance of rain inside the bin, inside each bin, the two bins of the first forecaster have no variance. Everything in the 100% bin is rain. Everything in the 0% bin is no rain. The second guy, forecaster 2, has one bin, 50%. Half of the days are rain, half of the days are no rain. That's maximum variance you can get with 0, 1 variables. Yes, it's a quarter. So the difference between the two forecasters is captured by inside bin variance, which is 0 for the first forecaster and 1/4 for the second one. Doesn't matter if you don't know why 1/4, it's a positive number. It's a binomial variance, Bernoulli variance, sorry. So far so good. If there are questions, I'm willing to, raise your hand or shout or something. That's what I'm here for. Okay. So now, okay, just some notations. You don't have to follow them, but just to show you that everything is trivial, okay? So let AT be the action at time t. Action is rain, no rain. And let CT be the forecast at time t. And let A bar of X be the average or the frequency of rain, the average action, in the days when the forecast was X. And that, of course, depends on the horizon, capital T. I don't know if you can see it, the horizon that we decided upon, okay? What's A bar T? Here is the formula for those who want formulas. Ignore it, it's clear. What's a calibration score? Is the distance between forecast and frequency, okay? Here is the formula, which is not what you expect, I think, but it is exactly equal to what you expect. Because what's written here, every period, look at the distance between the forecast at time t and the average for that forecast. Now, what you would like to do is the forecast is used a lot of times. It should get much bigger weight than the forecast that is used just once. But here we are counting periods. So if a forecast is used 50 times, you are going to have 50 identical terms here. So it's exactly identical to a weighted average of the distance between each forecast and what happened. Okay? Okay, just to show that I can write formulas. Then we want to talk about the inside bin variance. That has a name, a more civilized name. It's called the refinement score, okay? So that's the average variance inside the bins. Okay, you look at each bin, 20%, 40%, 60%, you look at the variance inside and average each bin with the right weight according to how many observations you have inside the bin. If you want to see the formula, that's the formula. But again, let's not dwell on the formulas. It's just to show you there is nothing fancy here. It's exactly easy, okay? Then there is another score called the Breyer score. Breyer was a meteorologist, by all means. So he said, forget about, no, he didn't say forget because there was nothing to forget at that time. He started it. He said, let's look at the distance between forecast and what happened. So if you said 20% and there was rain, it's 20% minus 1, 0.2 minus 1, okay? So just this, simple, okay? That's a Breyer score, okay? Very good. Now, you may not be surprised, but there is a beautiful decomposition of the Breyer score equals exactly refinement plus calibration, okay? That's a standard decomposition of orthogonal statistic, inside and outside variances. If you want a proof, that's a proof, but let's not dwell on it. Okay, so let's go back to the example. You see, we said calibration is 0 for both of them. Refinement is 0 for the first, a quarter for the second. So the Breyer score is 0 for the first, a quarter for the second. Okay? Very good. Now comes a little philosophy. We are talking about experts. Okay? How do we, experts are those that give us forecasts in this case. Okay? How do I measure how good an expert is? So there is a huge literature on experts, okay, which looks at the calibration score. That makes me very happy because I'm an expert. Yes, I can pass any calibration test, right? Remember, I showed you how to do. So I'm an expert on everything. Any forecasting problem, I pass the test, okay? So clearly, calibration is not enough, okay? And again, remember the example of the two forecasters. They are both calibrated, okay? But one of them is much better than the other. So what we are saying is, when you test experts, don't use calibration. That's too weak. Okay? Use the Brier score. Okay? That's a much better tool. Okay? Not the calibration score, the Brier score. Okay? Now, what's really expertise? Let me push this point. So what do you think about expertise? Is somebody who, when he looks at the data, recognizes patterns, recognizes regularities, okay, and partitions the days into bins which are very homogeneous, yes, that consist of similar days. That's exactly what an expert is. He knows this day is like those days when the chance of rain is 20%. That's a right bin, okay? So, of course, you want also the binning to be as refined as possible. The more expert you are, the more discerning you are, okay? All this is captured by a low refinement score, okay? The lowest refinement score when you have 0 variance in each bin. They are all alike, okay? So, okay, now let's go back. I can guarantee calibration, okay? But now, suppose I have a forecaster. Suppose I have a reference forecaster, let's call it. And suppose that forecaster has some expertise, but is not calibrated. So I can say, you are not calibrated. I'm going to calibrate you. Here is, I'm going to run my algorithm, the one I showed you, or zillions of others, by the way. There are many other algorithms for calibration. The problem is that if this guy had some expertise, I'm losing that expertise. Because calibration, remember, doesn't look at anything real, okay? Just looks at that graph and make sure that the track record is good, okay? So the question is, can I gain calibration? Now, gaining calibration in the sense of losing it. I mean, making it 0, yeah? So can I gain calibration, but without losing expertise, if there is some expertise there, okay? So let me make this more clear. Can I get K down to 0, but without increasing the refinement score? Can I get the calibration score to 0? Yes, I can. But that's a cost. The usual algorithms, they don't know about the refinement score, so the refinement score is going to blow up. Okay? So can I lower K, but without increasing R? Okay? Or let's put it another way. Can I decrease the Brier score by K? Okay? Sure, there is a way to do it. Simple way to do it, ex post. Ex post, what I do, I say, okay, here is the 20% bin. What was the frequency of rain there? 60%. Oh, so 20%, I meant 60%. Just correct ex post all the forecasts. Okay? Now that's cheating. Yes, we don't like that. Okay? What we want to do is this. Okay, so we can do this in retrospect. Okay? What we want to do it, that's a challenge, to do it online. Okay? I mean day to day. I want every day to give a forecast that will do what I want, okay? Will get me calibration, but without losing the expertise embodied in the refinement score, okay? Okay, so just to have some symbols, so assume that we have B. B stands for the bad guy, or for the one to be beaten, yes, for the reference forecaster. And what I want is that so B is the other forecaster. I am providing forecast C, okay? And what I want that my Brier score would be less than the Brier score of B minus his calibration score. I want to gain the calibration score, okay? Now, all these things, by the way, I'm writing this inequality. When I write such an inequality, and I won't do it again, yes, it means that I want this as t goes to infinity up to an error that goes to 0 and uniformly over everything, okay? Of course, I can achieve that, otherwise I wouldn't require it, yes? So remember that that's what we want, okay? So what I want is the Brier score should be less than, my Brier score less than his Brier score minus his calibration score, which is his refinement score, okay? We call this beating, that C beats B by B's calibration score. In short, Calibeating. That's a new word which we invented, and I'm very happy to say there are now quite a number of papers, mainly computer scientists, with Calibeating in the title. Okay? So I don't know if I have a mathematical contribution, but now I can claim that I have a language contribution, introduced a new word in the dictionary. Okay? So calibeating, again, means beating, not just beating, but beating by the other guy's calibration score. Okay, and again, it has to be guaranteed no matter what actions forecasts are going to be. Okay, so here's a picture just to make sure that everybody understands. So suppose that is the Brier score of the other guy, of B. Yes, so on the axis 0 to infinity, suppose that's a Brier score. Beating, just beating, means my Brier score is somewhere between 0 and his Brier score. Now his Brier score decomposes into the sum of refinement and calibration. His refinement and his calibration, okay? Calibeating means I want my Brier score to be here, okay? To be less or equal than his refinement score. I hope this picture clarifies what I want, okay? Questions? Good. Okay. Forget the example. Let's, okay. Now, again, in situations where things like the example, where things are stationary, it's easy to do that. But I want to be able to do that in a very general, non-stationary situation. Weather is arbitrary, it's not stationary, nothing, the forecasts are arbitrary, the binning doesn't have to be perfect like in the example we had. The mean averages do not have to converge. If they converge, I can go to the limit, yes? They don't converge, they can go up and down and do whatever you want. So I want to be in the most general case, and remember, online, okay? So, and guaranteed, no matter what, how the weather is, no matter what the forecast is, even if the other forecaster and the weather are correlating what they are doing, still, I want to calibrate the guy, okay? Can I do it? Well, if I wouldn't be able to do it, I wouldn't be here talking about this. I would talk about something else. So since I'm here, the answer is yes, okay? So there exists a calibrating procedure, okay? Okay, now problem is to construct it, yes? So there is in fact a very simple calibrating procedure. I'll tell you what it is. I like simple, okay? I'll tell you what it is. It's written here. Well, I'll tell you in words, okay? In words it says the following. I am now in period T. And let's say I want to calibrate. Can I use you as the big guy? Okay, Pradeep. Okay, he's a D guy, but never mind. So I want to beat Pradeep. Okay, I want to calibrate Pradeep. So Pradeep makes a forecast. What I'm saying, okay, Pradeep said 60%. Saying, wait a minute. When Pradeep said 60%, how much rain there was up to now in the days when he said 60%? I'm looking the past history. Let's say the answer is 42% of the days were rain. That's my forecast. That's it. That works. Okay? So my forecast is the average frequency of rain in the bin that Pradeep or the other guy is using. Okay? That's it. Now, by the way, our original proof was 5 pages of computations. Okay? After that, we had a theorem, and then I told Dean, very nice, that's a nice theorem, but this is not a proof. It's a proof of concept, which means now let's find the real proof. Okay? And we did find. And I'm going to show you that proof. Let's see, how much time do I have? I have to end at 20 minutes. Okay. The proof is short, you'll see. Okay? I think you'll learn something. Here's the proof. Everybody knows this formula for the variance. Okay? X bar sub t means the average up to capital T. Okay? How many people know this formula? I want to see a show of hands. Anyone has seen this formula? No? No? Good. I haven't seen it either before I found out, yes? So what's the difference between the first formula and the second? Here, you see here what appears is X bar T minus 1. It's the average up to yesterday. That's exactly what we want when we want to do things online. We know the average up to yesterday. We don't know what the average is going to be at the end of time when we do the checking. Okay? And you have to multiply by 1 minus 1 over t. Okay? Nice exercise to prove it. Okay? Now, okay, so you see the difference. Huh? That's the true formula exercise. Pradeep, in the break, you prove it. Okay, you get, that's your payoff for being the bad guy, the bad forecaster. Okay? Now, what's good about this? I can ignore the 1 over t term, okay? Just drop it. And since all forecasts are between 0 and 1, all the things are that, then my error is just summation of 1 over t divided by capital T, which is just log t over t, okay? That's something that goes to 0, okay? So I get that the variance is, instead of doing distance from the end of time average, you do distance from the current online average, and the error goes to 0 with t. Okay? So you have this nice thing that the variance is like the online variance, which is the variance with the tilde, that means online variance, up to something that goes to 0. Okay? Now, what's refinement? Refinement is average of variances. So the same thing is going to work. We just average over bins. Okay? So the refinement is like the online refinement up to something that goes to 0 with t. Okay? Now, what's the online refinement? The online refinement says you look at the distance between what happens at time t and the average of the bin, not at the end of time, but up to t minus 1. That's exactly what is called the average up to t minus 1 of the forecast bt that the guy used. Now, what's my procedure, if you remember? I'll remind you. My procedure says I'm going to forecast exactly that thing. The average of the bin that Pradeep used, that's my forecast. That's exactly how I define my procedure. CT is exactly this thing. So what's written here is nothing but this expression, right? But this is my Breyer score. So my Breyer score is the refinement score of B up to something that goes to 0. End of proof. Easy enough? And I didn't cheat. Believe me, I didn't cheat. Okay? There's no cheating here. There's nothing hidden. What you see is what you get. That's the entire proof. Questions? Okay. You are either asleep or surprised or whatever. Okay. Yes. Okay.
Hi. But if I don't know how the market for forecasters work, if they feel that they're being ranked by the population according to a scoring rule or something like that, would Professor Dubé perhaps misreport the weather on purpose to?
Very good question. And I say very good question in two cases. Either I have no clue what the answer is, or the answer is coming. We are in the second case. Okay, so thank you for the question. No, I mean, it's a question that it is indeed a good question, but it's coming. Okay, so keep it, and if I'm not answering it, you can ask again. Okay. Now, Calibeating. Remember what Calibeating is. Okay, I'm repeating the theorem that we had. Okay, it says use the average of the bin of B for his forecast as my forecast. Okay, and that guarantees that I'm calibrating B. I just proved that. Okay, now let's do a crazy exercise. Okay, let's try to calibrate myself. Let's self-calibrating. It's not a new age religion. Yes, it's not something like that. We'll see what it is. What's self-calibrating? I want to calibrate myself. So let's just formally, instead of taking B equals C and just replacing every B by C. Okay? So then that theorem becomes this theorem. Okay? Just replace formally B by C. Okay? Assuming I can do that. I don't know. Well, who knows? Maybe. Okay? But then what does it mean? It means that B of C is less or equal than B of C minus K of C. Okay? That's an inequality that exactly says the same as K of C equals 0. So self-calibrating is just having calibration score 0, which means being calibrated. So self-calibrating is nothing else than calibration. So let's take this and see if we can do it. So in order to do it, I have to do the following. I have to give a forecast C so that the average up to yesterday of the forecast C is going to be exactly C. Okay? That's a fixed point kind of requirement. Can I find such a fixed point? Well, if A bar is a continuous function, but A bar, remember what A bar is. A bar is exactly the graph that I showed you. It's a discrete function, finitely many points. It's completely arbitrary. It's not continuous in any sense. It's arbitrary. So I cannot get that. So can I get that approximately? Okay. So what we want is to have CT to be close to a bar of CT. We call this an approximate fixed point. And there is a neat theorem that says, look, you cannot find such a point. You cannot even find, by the way, if you're thinking of approximate fixed points as saying something where, suppose I have function f, fx is close to x. No. Think of the function that is 1 up to a half and 0 after a half. There is no point that is an approximate fixed point. Okay? Approximation comes in a different way with probabilities. Okay? So here is the statement. Okay, forget what it says. Okay, that's just what we need. But essentially it says there is a probability distribution so that on average we get a fixed point. Okay? And okay, sorry. Sorry, I meant to jump over that. Okay, never mind. Okay, we don't want to, so we can prove this with Brouwer, wrong tool. We prove it with a minimax theorem. That's another minimax. Not as nice as the first one I told you, but still a nice use of the minimax theorem. So the existence of this is obtained by solving a minimax problem. Okay, so one can get a stochastic approximate fixed point using the minimax theorem. Okay, once we have that, forget this, we plug it in the previous theorem, we can get a probability distribution over forecasts so that CT on average is close to a bar of CT. So we satisfy that condition and we just get exactly what we wanted. A probabilistic procedure that gives me self-calibeating, which means calibration. Okay? So here's another way to get calibration. Okay? So again, self-calibeating, we get calibration, but we have to invoke every period we have to solve a minimax problem that gives us the probability distribution on forecasts. And again, that should not be a surprise. There is no deterministic calibration. You can only get this with stochastic ones. Okay. Yes? Trivial. Minimax problem is polynomial. And the number and the size of the problem is trivial because it's just the size of the grid. Okay, now again, if you go to many dimensions, grid also increases. Computer scientists have some tools to get this better. We can discuss this later, okay? But minimax is not fixed point, okay? It's not Brouwer. Minimax is a triviality relative to fixed point. Okay, very good. Now, here's another thing someone may ask. Look, I'm calibrating Pradeep, but nobody says that I'm calibrated. If I'm not calibrated, then Hervé can calibrate me, right? And if Hervé is not calibrated, then Shmuel can calibrate Hervé. And we get into this big sequence of calibrating. But if when I calibrate Pradeep, I myself calibrated, that's the end of the line. Can we do that? Answer, yes. Okay? There exists a stochastic procedure that guarantees calibrating B and being calibrated. And it's a complete triviality. What you have to do is you just look at the joint binning defined by my forecast and Pradeep's forecast and apply the previous theorem. Okay? So I said, once you understand what's going on, everything is trivial, but you know, you need the right insight. Okay. Let's ignore this. Let's ignore this. There is a lot of other things. Like, okay, now suppose each one of you guys have a forecast. Okay? Can I calibrate all of you? Yes. Can I at the same time be calibrated? Yes. That's called multi-calibrating. Okay? How do I do that? Very easy. I just look at the joint binning formed by all the forecasts here. Okay? Now, there is a dimension problem here. There are ways to go around it. But conceptually, that's the idea. So you just look at the joint binning. Okay? So a cell is forecaster 1 said 10%, forecaster 2 said 12, forecaster 3 said so on, so on. You look at this binning and you just apply the previous theorem. Okay. Now, let's see. Okay. One thing again, game theorists may not worry much about it, but it's an important distinction that we made in one of our papers, is that there are two parallel worlds, but very distinct. They are not really parallel, they meet in dimension one. In dimension one, fixed point and minimax are the same thing. It's just the intermediate value theorem. If you remember your Brouwer fixed point, in one dimension is just the intermediate value theorem. It's exactly like the minimax, they are the same. Any dimension from 2 on, those are very different worlds, okay? And if you want things to be deterministic, you need fixed point. You need hard work. If you want things to be, if you allow things to be stochastic, minimax suffices. Okay, and there is a lot of discussion on that, but it's an important topic and it's an important distinction, and that helps to understand what's going on. Okay, now I think I'm going to say something relevant to your question. Maybe yes, maybe no, you'll tell me. So, refinement score, what is the refinement score? Okay, I claim, so remember what the refinement score is. You are just looking at the variance in each bin. Well, if the bin would be labeled with exactly the average of the bin, okay, if I change the label of the bin and put exactly the average of the bin, okay, then the variance doesn't change. The variance doesn't care about what the label of the bin is, okay? But now I get exactly the Breyer score, okay? Because it's a distance between what's in the bin and what the label is, between forecast and action. That's A minus C. Okay, so what this means is that refinement score is nothing else but the minimal Breyer score that you can get, allowing any possible relabelings of the bin. Okay, and of course, the right relabeling is the one where you put just the average of the bin. Okay, okay, that's a formalization. But again, think about it for a moment. Again, refinement only looks at the variance of the bin. Doesn't care what the name of the bin is. If that was a 20% bin or the 40% bin or the 100% bin. Just looks what is the variance inside the bin. Okay? If we put the label to be exactly the average of the bin, we get the Breyer score. Okay? Why is this important? Okay, here I'm going to jump because I need to finish on time. I forecast that the chairman will not allow me extra time. It's a calibrated forecast, yes. Okay. So, as I said, there is a whole literature on experts. There is a whole literature on combining experts, on being the better expert, on being the stronger expert. All this literature usually, I mean, as far as I know, deals in the space of linear combinations of experts. They don't go beyond linear combinations, okay? So Calibeating always looks at all possible relabelings, whereas all this stronger expert literature looks only at linear combinations. So Calibeating beats the stronger expert. It's better, okay? Calibeating is a better notion than all those better experts, stronger expert in the literature, okay? Calibeating beats stronger. Okay, I promised you something new. Here is something new. I have 5 minutes, right? Okay, 3 minutes, 3 minutes. 2 minutes for questions. How much? Oh, 4, okay, I got it. Okay, no, I'm not going to get into details, okay? Everything up to now has been done with a quadratic distance. Why? Because statisticians told us that with quadratic things work beautifully. You get all these beautiful decompositions with L2 norm. That's why calibration plus refinement is Breyer. So quadratics are so neat, right? You have all this orthogonality, everything works beautifully. But life is not quadratic, what can we say, you know? I mean, there are things that are not quadratic in life. So the question is, okay, so scoring rules, okay, we can look at the quadratic loss, which is action minus calibration score, okay? What's the beauty of that? If the action comes from a probability distribution, what is the best forecast, C? It's the average of the distribution, right? I mean, the variance is minimized when you take the expectation as, yes? Okay. In general, there are things that are called proper scoring rules that have the same property, that they are minimized when you forecast the right thing, Okay, so there are many such proper scoring rules. Then there is something called divergence that is defined by that. I'm not forget all the details. Okay, you can take any proper scoring rule, for example, logarithmic, that gives the Kullback-Leibler divergence, and there are lots of other proper scoring rules. Okay, and for each one of them, you can define the Breyer score, you can define the calibration score, you can define the refinement score. Everything works okay. And then I can define something called proper calibrating or proper calibration. What's proper calibration? Means I want my procedure to be calibrated not just for the quadratic scoring rule, but for every proper scoring rule. Well, there is bounded, let's say bounded, and the one is just normalization because multiplying by 7, everything gets multiplied by 7. Okay, so proper calibration means I want to be calibrated no matter what scoring rule you are going to use. Okay? With one procedure, not for each procedure, not for each scoring rule I want a different procedure. I want the same procedure. Okay? Uniformly in the scoring rules. Okay? Okay, those are formal definitions, forget it. I mean, just an extra supremum at the beginning on the scoring rules. Okay? So, here are the results. If I have calibration, I have proper calibration. If I've succeeded in doing calibration, then same procedure is going to be proper calibrated. That's a neat result. Okay, second result, if I have Calibeating, I also get proper Calibeating. Okay, right? Now, those who took classes from me will know that when I say the second time right, that's wrong. This is not true. Okay? So whatever works for calibration does not work for Calibeating. Something can be Calibeating for one scoring rule and not for another. Okay? But if you remember, we were talking about Calibeating the joint. That thing turns out to be proper Calibeating. Okay? Okay, forget that. Then we have something that we call properly Calibeating, which is short for Lipschitz proper Calibeating. Proper Lipschitz Calibeating. It's properly Calibeating. Okay, well, not everybody appreciates my puns. Okay, never mind. Proper multi-Calibeating. Okay, why is it important? Let's go back. Okay, my last slide. Sorry, my last 2 slides, but there is a joke at the end, so that's my last slide. Doesn't count. That's a free. So think about, why do we want forecast? Bayesians don't need forecasts, right? Because Bayesians, they know what the probability of everything is, and they just maximize expected utility, right? Us mortals who are not Bayesians, or mortals who are not Bayesians, and don't have a probability distribution over everything, that's what's called decision-making under uncertainty, because we don't have a probability distribution, rely on forecasts. Okay, we use a forecast telling us what's the probability that A, B, C, D will happen, and we use that and we maximize utility, best replying to those forecasts. Okay, so that's decision-making under uncertainty, and okay, that's a formulation, but anyway, the optimal decision is to maximize expected utility given the probability distribution on the state of the world given by the forecast. So that's what I call best replying to forecasts. Okay? Okay, now turns out, okay, I'm going to jump over all this. Okay, I'll just give you the bottom. Sorry, I'll jump over all this. Okay, I'll just give you, here is a slide. Okay, turns out that proper calibration is equivalent to universal no regret. What universal means is all utilities, all bounded utilities, okay? They're just bounded, nothing else, no assumption on the utility functions. So having no regret, that's exactly what proper calibration is. And proper calibeating means that you improve the average utility that you get as high as you can. Okay, so that's the neat connection between proper calibration and proper calibeating and decision theory. That's exactly what we need for decision theory. And that works uniformly on everything. Okay, and I think that's the end. Now, what does every forecaster deserve? A proper calibeating. Thank you. Okay, any questions? Ken?
You're thinking in a world of binary situation, right? Rain and rain.
No. Sorry, that was just examples. It works in arbitrary dimension. I can have
So
rain and shine and anything, as many dimensions you want.
Finite.
Yeah, finite dimension, yes. We are still finite dimension. I'm pretty sure things can be extended. But again, one has to be careful. If the dimension increases, some of the things become, because let's say the grid size is exponential in the dimension, then there are some computational issue. But computer scientists, I have some tricks to get rid of that. I think Kostis and his co-authors have some ways of doing these things in a much more efficient way. We also have, okay, so yeah. Oh, okay. So I stay here, right? Okay. You want to put your Hervé? You want to put your slides or something? You don't have slides? Yes. Okay. So you have. Okay, 1 minute. Okay. Change of guard. Change of guard. Okay. Just can somebody? Hello? Can you? No. Okay. We are back on track. So it's my great pleasure to introduce Hervé. Hervé and I think, started more or less at the same time. We were young kids, doing game theory. And Hervé's being, everything happening in game theory, Hervé was there, You started with zero-sum games, if I remember your PhD. Equilibrium, dominance, cost, fairness, social choice, voting, and that's only an epsilon of what Hervé did, yes? So it's really a great pleasure to have Hervé here, and I think that we should give a big round of applause because Hervé also has a birthday today. I won't say how old he is, because then you'll get... So, bon anniversaire, n'est-ce pas? Bon anniversaire.
Okay. Merci. Thank you, Sergiu. Indeed, a state secret. My age is now a state secret. All right, I'm going to talk... Yeah, it is written there. Okay, so compromise in collective choice. This is a talk about social choice, the standard, if you want, voting context, but I want to put a different spin on something. So it's joint work, in fact, in progress too. So I start with the beginning, which happens to be 3 French people, but there is no bias there. It just happens to be like that. Rousseau said 1762 was the first to push this idea that the will of the majority is really what a democracy means. It's a very powerful idea. I mean, especially when you think of the context. So, of course, Rousseau was just saying that what the public authority should be, really to respect the will of the majority. And then Condorcet said, okay, well, let me make that precise. If I put a little model in which I see the options and the preferences, well, the will of the majority is what we call now finally select the Condorcet winner, right? And he was very well aware himself of the fact that this may not exist, but still it's a powerful concept. No. I'm saying Rousseau defined the will of the majority. I mean, as a philosopher, define, right? Okay. And but then Condorcet say, okay, this is what it is, all right? And then Tocqueville, who is kind of, if you want, early sociologist, says, well, I mean, he's also an aristocrat who really didn't like too much this idea. I mean, well, the majority can be tyrannical. I mean, that's the expression we use now. But that is, you have situations where the majority of 50 plus epsilon% imposes its will on a minority of 50 minus epsilon%. So, yeah, and indeed, the Condorcet winner approach, anything Condorcet consistent, does not leave room for compromises when you have like that two antagonistic blocks. Nevertheless, despite these two objections, absence of Condorcet winner and the fact that it is not compromising, we accept that wholeheartedly, and because in most democratic political elections, we use Condorcet consistent rules or rules which in many ways are trying to respect the will of the majority. I mean, if you start by plurality, yes, technically speaking, plurality is not Condorcet consistent, but if a candidate receives a majority of the vote, it is elected. So I abuse notation a little bit by saying plurality is Condorcet consistent. Technically, it's not, but it's still the idea of the majority, right? And it still will fall subject to the kind of criticism that Tocqueville was mentioning. And we live with it. I mean, we have all the time elections which are, razor thin in the US, in every country. I mean, you have this situation and we accept them because we feel we have to. Okay. And you see on other methods, I mean, they all have some. So my point here is that this is fine for political elections, but it's not for situations where we are not trying to identify one particular outcome, one party in power, one person to use a certain position, but we are instead trying to reach a compromise between a number of different parties with their own views on the situation. So essentially here, what I'm referring to is a situation of bargaining as opposed to one of voting, right? I mean, when the essence of bargaining is we compromise. I mean, that's the point, right? So what I want to start with is a couple of examples where the thing will be, yes, those are situations when we want to bargain, but maybe, but there are those situations where we want to do something like bargaining, but not in the strategic way that we are used to think about, where we actually sit on the table and so forth, but in the mechanical way that is allowed by voting rules, social choice rules, and things like that. So, and this is especially useful, this is going to be especially useful when what we call the agents of the voters in the traditional context are in fact not humans. I mean, they are not the real party. So let me give a few examples. You can, I'm happy to have objections here, but we pick a restaurant but between a group of friends. Okay, if someone has a strong objection to one type of restaurant that makes him or her sick, we make the compromise. We don't think in terms of, well, I mean, 5 of us want to go to a very spicy Indian restaurant. Too bad if the other 4, right? Okay. So a new colleague in the team, I mean, that's a bargain. You can say, yes, there is a way to solve that without a voting rule. Just sit down and bargain. But what I want to do now is to show methods in which you try to achieve the compromise without having to actually sit and bargain, but just by reporting preferences or rankings derived from a certain number of criteria. I mean, think of the third point here, the winner in a multi-event sport competition. This nice article by Kondratiev and Nesterov. This is the situation where you have to select a winner, let's say in a ski competition or, multi races competition. So you have a first race, and then there is the winner, the second, the third, and then you have a second race, and another person is the first, second, third. And then after they all run all these races, you have to decide who is the overall winner. So who are the voters here? Well, the voters here are in fact the scores that the rank that they obtain in the race. So they are not the agent. I mean, the voters are an abstract thing. They are not the person that we are concerned with. We are concerned with the person who are outside of the model and are saying, look, I mean, I think that given that this sportsman, I mean, they got this rank, I mean, this is the one who should win, right? So you see what I'm saying? We are trying to make a systematic way to solve this kind of problem. I have to select a decision based on a number of criteria, which are abstract criteria not connected to a particular person, and I want to do that in a way which is mechanical because the number of people involved is too big. It's not practical to sit together around the table, just like in political voting situation. We don't expect to sit around a common table, right? So a hotel for my next trip. That's a very nice paper by by more than 2 computer scientists, where here the situation is you are a single decision maker, you are deciding where you're going to reserve your hotel in the next trip that you do, and you have a bunch of criteria. There is the price, location, comfort, what's the quality of the Wi-Fi, you have those things. So, and you have a bunch of choices of your hotels, and well, maybe there, I mean, the claim is that here you are not going to use a Condorcet winner type of approach. I mean, if you see that one hotel has a horrible, very noisy club that is making a lot of noise through all night, that's terrible in terms of the context. Okay, that's an elimination. That's a veto. So what we are led to, if we think in terms of bargaining, but again, formal bargaining sustained by rules a la social choice, I mean, exactly in the context social choice, is we try to have these 2 dual concerns, choosing the best outcome for many agents and eliminating the one that some agents really dislike, right? And in fact, this is something that you find in many in many of the actual social choice rules that we think of. Qualified majority is something which goes away from the Condorcet winner precisely to avoid situation where the final decision is decided by a very thin margin. Also Borda gives a positive and negative point if you want, because you have a low score, that's a way to penalize you and so forth. Okay, and now there is a recent literature which actually, recent and not recent, the original paper of Muller voting by Veto, but things like the recent stuff, the recent rule, plurality veto rule, it's something which came up in the literature on voting from a different perspective, but it combines in a nice way a first round of plurality followed by a round of voting of veto. I don't have time to go through that, but you will see the sort of idea that... okay. All right, so basically the model will be a general social and collective choice problem, namely deciding a public decision based on a bunch of individual parameters, individual rankings, where in fact, in order to be able to apply this to interesting economic models, the set of agents and the set of outcomes will both be infinite with a standard topological structure. And we will define a rule, a strategic rule, strategic between question mark, just like the Condorcet winner is the stable, picks the stable outcome of the majority cooperative game, right? Except that in this model of voting by veto, we'll define a rule, a game, a core stability game in which there will always be a stable outcome, as opposed to the Condorcet winner. But in fact, the counterpart will be that there will be more than one stable outcome. So as a counterpart to the Condorcet approach, which is, very deterministic but may not exist, here it's going to be, it's always possible to do that, but you could expect more than one outcome. And that's why you think of the rule as a short list. Sorry for the typo. Compromise exists, and they will be identified by the rule, and the rule will provide, in many cases, a short list of options, not a final option. Okay. All right. So this is the model. N is the set of voters. A is a compact set, a set of outcomes. They are both compact subsets of some Euclidean spaces and we have ordinal preferences by individual agents over the set of outcomes. And I will represent them for the sake of convenience by doubly continuous utilities, U of I and A. So this is the utility of agent I over outcome A, but the whole thing, the whole concept and results is purely ordinal, right? It's just that it's so unpleasant to use other notation than utilities. So there will be a way to count voters. This is the positive measure lambda over the set of agents, and therefore lambda of S will be the relative size of the coalition S, because this is a unit measure. I'm not thinking of a large number. I'm thinking of a positive measure of mass 1. And when I say lambda of S is 1/2, it means it contains half of the voters for this measure. Of course, the measure is arbitrary otherwise. And similarly, there is a measure of outcomes, of the set of outcomes. And both can have countable atomic and non-atomic parts. So in that sense, they are very general. Okay. Condorcet winner, well, I don't need to go through that. I'm just here redefining the Condorcet winner because I have a continuous model. So Condorcet winner is that the mass of those agents who prefer A to any other outcome should be 1/2. you know, this is just to introduce the notations. Yes? No, I mean, I don't, you know, I'm not paying attention to that. Okay, now the key for the veto approach can be and should be, I think, presented from this, from thinking about a polarized choice case, a case precisely when the polarization is such that you feel that, I mean, you don't really know how to make the arbitrage and, you know, where to go. And here we will do it in a way which will not be the majority way, because we want to take into account the need for compromise. So imagine that we can partition the set of agents and the set of outcomes in such a way, I mean, N1, N2 for the agents, B1, B2 for the outcomes. And I have a situation where for the agent in NI, anything in BI is better than everything in BJ. So it's a purely very clear, for all the outcomes in BI and BI are better than those in BJ for all the agents in I. And of course, NJ for BJ, okay, for BI. So this is, you know, clear division in two blocks over the set of outcomes. Now, we have two criteria which are sort of pushing in different directions. If BI is bigger than BJ, that there is more outcomes in BI than in BJ, we think that NI is accepting more outcomes than NJ. It's being more compromising. I mean, this is going to be the compromising direction, right? On the other hand, if there are more agents in NI than in NJ, if lambda of NI is bigger than lambda of NJ, then since NI is larger, the NI's opinion should count more than NJ's opinion. That's the majority ID, but here I just say it goes in that direction. Yes. So, oh yes. Oh no. Absolutely. It will have a, yes, it will be used like that. I mean, okay, so if the two inequality go in the same direction, like here, I'm fine. I would say, yeah, NI-BI is better. So let the coalition NI gets his way, and the outcome should be in BI. Okay, but what if the two things go in different directions? Well, there is a simple observation due to the fact that here I'm talking about relative shares of the number of agents, relative number of agents, relative number of outcome. If I take any aggregation index, W of lambda of Ni and mu of Ni, a way to aggregate the two indices, size of the supporter Ni and number of outcomes in what they support. If I take any such symmetric and monotonic index to say that the index is better for N1B1 than for N2B2 is the same as saying that lambda of N1 is bigger than mu of B2. Right? Or equivalently, lambda of N2 is bigger than mu of B1, is less than mu of B1. Okay? Yes? Yes, all between 0 and 1. They are unit measure. They are the relative size. These two numbers, those two numbers are between 0 and 1. It's a size. That's the point. That's the whole point. Okay. So now, here, yes? Another question? No? Oh. Now here comes symmetric. That means that the two W is symmetric in A and B. W of AB equal W of BA. And that's a simple, you do the product, then you do the sum, and you realize it's the same, and then it's a very simple observation, trust me. I mean, there is nothing, But it's just to say that now that this is the property that will strongly take us in a direction which has nothing to do with majority voting and with, in fact, go to this idea of core stability in the veto sense. We will say that if lambda n1 is bigger than mu of B2, then we should choose only in B1. So in other words, lambda n1 bigger than mu of B2, we favor systematically the group n1, okay? Because, as we said in the previous slide, you know, for any way of aggregate, any symmetric way to aggregate these two indices, and the n1b1 pair wins. And also another aspect is it may happen that we have equality. Those two W for 1 and W for 2 are equal, in which case we will say that we should choose at least one in B1 and at least one in B2. So you see, we already are incorporating here the fact that the solution sometime will have to be multi-valued. I mean, that's normal when you do compromise. I mean, there are situations where you will not be able to break a symmetry. Effectively, what it means is a power to veto, a veto power. Because what you are saying here, you know, when you say, oh, if lambda n1 is bigger than mu of n2, so it means that the size of the coalition n1 can eliminate those outcomes in B2 if they happen to see them or to pretend that they are at the bottom of their own preferences. That will be enough to eliminate them. So you are effectively defining a veto power with those two measures, lambda and mu. And this, of course, leads to the definition of a cooperative game, the cooperative veto game, which is defined by the model. And the key notation here is U of SA, the upper contour of the outcome A, which is for all the members of coalition S. So U of SA will be the set of outcomes such that everybody in S prefers those outcomes to A. Okay? Yes? Yes? Yes. That's exactly it. Exactly. And 70% can eliminate 30% by simply saying they are at the bottom. Absolutely. This is yeah, but even if they don't agree absolutely, they still have the power. And the question is, you know, what about that cooperative game? And in fact, that cooperative game works very well. So here, instead of writing it like, well, instead of writing it lambda of S, see, what's the opposite, what's the contraposition, the negative of this inequality? If lambda S plus mu of the U is strictly more than 1, it means that lambda S is bigger than the set of all the outcomes which are below A for at least one person in S. So in other words, by eliminating the complement of U of SA, the agents guarantee that the outcome will be A or something better than A for all the coalition. And what you end up with here is that this veto core, and this is the definition of the core, which is, you know, with full generality for lambda and mu. And the theorem is that this thing is never empty, is a compact and typically multi-valued subsets of outcomes, and it selects efficient Pareto optimal outcome because in particular the grand coalition has the power to eliminate anything it wants, so right, and it meets the binary compromise property. Okay, so this is in fact a generalization of a concept that I wrote about in 1981, so not exactly yesterday, where that was applied, first of all, in a way that was systematically symmetric vis-à-vis outcomes and vis-à-vis agents, and in the context where both the set of agents and alternatives was finite. Okay. All right. So now, if you think of the choice rule that this veto core will define, it is nicely behaved. In particular, well, there is first this upper continuity property, which is not a big deal. I mean, just that the fact that the graph is closed. But the second one is more unexpected. It is actually masking monotonic, just like the Condorcet-Wiener correspondence. If you think of the Condorcet-Wiener as a correspondence which sometimes is empty, it is masking monotonic. Meaning that on the one hand, it's monotonic in the usual sense. You raise the position of one outcome somewhere, and if that outcome was in the set, it remains there. But also, that this is a very strong part of the property of masking monotonicity is if you reshuffle above, if you consider an outcome and you reshuffle the outcomes above A in the preferences of all the individual agents, and reshuffle below A, you will not change the fact that this outcome is still in the selected set. So if it's a Condorcet-Wiener, it's still the Condorcet-Wiener, and here it remains there. What's interesting is that this correspondence also satisfies a property which is normally associated in social choice with scoring rules, which is the so-called population consistency. I mean, this becomes a little bit more technical, and I don't want to spend time, but essentially what the property of population consistency says that if for a given set of outcome A, a particular outcome small a happens to be chosen for a first group of agent N1 and also for a second group of agent N2, both groups being disjoint, then it will also be chosen when you put together these two groups. And this was the key property that Peytonian used to characterize a scoring rule. So it's a bit surprising to find it here. Okay. Yeah. There are some issues in the definition, you know, to try to do, but let me skip that one. I mean, we can, okay. There is also a half characterization of the veto core, which is that a choice rule will meet the masking monotonicity and the binary compromise set only if it is a subset of the veto core. So you are capturing here any rule which satisfies these two axioms. This is actually not a complete characterization, and I certainly don't want to spend time on it, because now all I want to do in the time that remains to me, which is super, I want to show you some nice example. I want to show you how that thing works, because it turns out really that they are, I mean, okay. It works in interesting ways. There is also, at the end, a theorem, but it's more important to, okay. Shortlisting rule, why is it? Let's illustrate. Let's take the standard bargaining model and apply it. I mean, you know, standard bargaining model as introduced by Nash, you have two agents, a compact set of outcomes, and continuous utility map A into a bargaining set, and we have the standard convexity type properties and so forth that gives you a story like this. We have my set of feasible outcome. I have the Pareto frontier. The little indifference curve corresponds to the Nash point. Then you have also this diagonal, which is actually picks the Kalais-Morodinsky solution. And what I've drawn here in the shaded areas are the two regions that the veto core eliminates. Why? Because each person, this is a case where the set of agents is discrete. There are two agents, each one is of weight 1/2. And each one can eliminate 1/2 of the outcomes. And here the measure of outcome is the measure, the standard Lebesgue measure. We could choose another measure. Yeah. But you could choose any measure you want. You see, that's the point. it's useful to do it like that to connect with the model of axiomatic bargaining, but any other measure would do. So if you take for that measure the Lebesgue, what happens is if you take the vertical line and you think of what's the subset on the left, which is fully shaded, and the subset on the right, I mean, this line cuts the area in two parts vertically. And similarly, horizontally, you cut the area in two parts of equal size, equal area. And the remark that you have the Nash and the Kalais-Mrodzinski is in fact a general fact. You will always capture like that the Nash bargaining solution and the Kalais-Mrodzinski. Questions, does it work also for more than two bargainers? Say that again?
Sorry, can you iterate this? So after you've eliminated the shaded regions, can you do it again?
You certainly can, and then it's reminiscent of the Luce and Raifa. There is a Luce and Raifa bargaining solution introduced by them, which does the convex combination of the two utopian point for the two agents and then reiterate. So it's the same thing in the same spirit, but then it's I don't know what that rule is. In a certain sense, this is not my concern, because it's going to give me a selection of the Veto core, but I will not have an interesting grasp on it. What I want is something continuous, and that can be Veto core is only the Pareto frontier. Yes, absolutely.
Just the Pareto frontier, so you
yes. We could, but we could decide arbitrarily to do it again. But anyway, that's not the spirit. Yes, you're absolutely right. I mean, the Veto core is the Pareto frontier, that part of the Pareto frontier. So it's a scale invariant multi-valued bargaining solution. It contains these three things. I mean, the equal area is another solution. And we can prove that it works for n equal 3, but it's hard, and hard to see if it's going to work for larger n. We believe it's true, but it's tough, because you have to do... Yeah. Just that it contains... You see, this is not the most important example. The important example come now. IMBY. I will do IMBY and NIMBY. You remember NIMBY? Not in my backyard. And I start by in my backyard. So I have a location problem, which is the canonical, if you want, public decision problem on a line. And in one case, I have a situation where we need to locate a facility or choose a point on the interval, and everybody has single peak preferences over the location that will be chosen. And your utility is your distance to the location. Sorry, your disutility in the IMBY problem is the distance to the facility. You want to be close, so your distance, your utility is really minus the distance. You want to be close. The important point, of course, is that preferences are convex and so forth, and things will work well, in particular for the Condorcet winner, right? So an agent I is identified with its peak because I assume for simplicity, so that computations are easy, that the preferences are single peaked around are symmetric around the peak, so it's just a normal distance, your disutility, and therefore the description of the agent and the mass of agent is simply a unit measure on the 0,1. And I compare that, I mean, the mu, for instance, here is uniform in 0,1. It could be, again, anything, but to get those figures, we do that, okay? So start with the case of maximal polarization. The measure lambda is the population is split in two parts. One we speak at 0, one we speak at 1. and nothing else. You either are completely leftist or completely rightist. So lambda 0 equal Q, lambda of 1 equal minus Q. The Condorcet winner and all scoring rule will choose 0 or 1 according to which one of Q, whether Q is bigger than 1/2 or less than 1/2. Here the veto core very easily, because by this interpretation that we had before, if you have a fraction Q of the outcome, they can eliminate the fraction Q that they like least, and which will give them 1 minus Q or closer. But then the others have exactly the same power, symmetrically, and therefore the veto core in this case is the unique compromise at 1 minus Q, where you go. So it's nothing. It's not a surprise, because in a sense this situation is the epitome of where you want a compromise versus a purely polarized thing. Now it looks good. It looks good here that you have a single outcome, but this is really a special case, because for any other profile of peak, anyone, as long as you have more than one, more than 2 locations extreme like that, the veto core will be a non-trivial interval. It will be an interval, and there is no, and it will be an interval that may or may not contain the Condorcet winner, right? It's just a little remark that it will always contain a version of the Condorcet winner in which you put n-1 phantom, in the discrete formulation, some phantom voter or fixed ballots uniformly. That's a detail. In fact, it's really not part of the discussion here. So, okay. So, very simple. Very simple. And now is the one which really personally convinces me that we have something interesting here. Interesting in terms going beyond just the mathematical elegance of this general existence result and what it says. Okay, so now it's the NIMBY problem. Not in my backyard. It's a bad facility. We want it as far as we can from where we are. So the distance from my peak to the facility is my utility. Again, symmetric preferences. This time they are called single-dipped. And that's the technical thing, because it's this utility is a convex function, and therefore the preferences are non-convex, and the upper contours are not convex. And in that case, like in the previous case, the Condorcet winner is whichever of the 2 endpoints is preferred by the agent with the median peak. Let's go back to the IMBY problem, where it's well known that if you want to be as close as possible to the location and you have single peak preferences, the Condorcet winner is at the location of the median voter. But here, what does the median voter think? He looks at the 2 extreme, the 2 endpoints of the interval, and he's interested to put the facility in this endpoint, which is the furthest away. Now, clearly, all of those who are to the right of the median voter will also want to go to 0 if that's what the median voter wants, and so forth on the other side. So you're still saying the median should choose. This is bad. This is bad for 2 reasons. It doesn't pay attention to the fact that the endpoints can be locations which are very busy with a lot of people, right? Precisely if you take the extreme situation, Q, 1 minus Q at the 2 extreme, and those 2 numbers are very close, you don't compromise in a really bad way, because you end up pushing the worst outcome like before. But there is something more that you will see in the next slide. Okay. For the case of the veto core, it may also choose an endpoint, but only if that endpoint is not not too busy, as we will see in the... Okay, so now here is the important numerical example. If you don't buy that one, then I have not done a good job. What I want to say is that in this particular example, the Condorcet winner type, the Condorcet winner solution is really atrocious. It really makes no sense. Why? Okay, so what's the numerical example? I have a density, so the agent now is 0 to 10 to have simple numbers to read. So that's the interval from 0 to 10. And here I write the derivative, the density of my distribution, my measure of agents. So in other words, I have 3 groups of agents. The first one, 3 groups of agents, one which is uniform from 0 to 2, one which is uniform from 4 to 6, and one uniform from 8 to 10. Each one is 1/3 of the agents, and it's all very symmetric, right? Because between those intervals, there is nobody. So you agree with me that because of the perfect symmetry of the situation, we have 2 Condorcet winners, 2 weak Condorcet winners at each end, because the median voter is at 5. There is exactly the same number of people to the left of 5 and to the right. But both points are Condorcet winner, and this is a knife edge case. But think now, not of the knife edge, but the little deviation. Suppose I push a little bit 4, 6 to 4 plus epsilon, 6 plus epsilon. Tiny bit. Now, immediately the unique Condorcet winner is 0, right? Because I have created for my median a slight incentive to prefer 0. The thing that's really horrible about the situation is that the median is now choosing between 0 and 1 when she couldn't care less about whether it's 0 or 1, because she is essentially at the middle and the shift in utility is negligible. So you have this situation of discontinuity where it's not just the fact that a small change in the parameters affects the outcomes in a brutal, discontinuous way, but this particular change of parameter of the solution is caused by a change in the preferences of an agent who is essentially not caring about one or the other. You see, so in other words, little, tiny bit of lack of imprecision in the measurement in the interval 4-6 could have dramatic consequence when those people do not care one bit about it. The Veto core here. No. Yeah. But here, what we will show, the theorem later, is that this multi-valued correspondence is also lower hemi-continuous. Oh, sorry. No, I take that back. In the case of convex preferences, the result will be that when there is a multi-valued Veto core, it is also lower hemi-continuous, therefore it behaves well. But for this case, you're right. I mean, you will also have discontinuity. But the point, the big difference is that you are not trying to choose between 0 and 1. You're just saying, look, 0 makes sense. I can apply the test. It works. 1 makes sense. 3 and, the 1/3 from the left makes sense, 2/3 from the left makes sense, and if I move 4-6 to 4 plus epsilon, 6 plus epsilon, all these numbers will shift a bit, okay? And sometimes, I agree that sometimes there will be a disappearance of one of them and the reappearance of the somewhere else, because this is a problem with non-convex preferences. Okay, and to give a second example here, this is an example where you have, in fact, a single outcome, but that's a single outcome in the Veto core. But here is the characterization, which is not very difficult to pull out, but still a little bit of work. In this general NIMBY problem with the way I've described the preferences, the Veto core, in fact, systematically select, I mean, typically, generically, a finite set of points, and those points are selected by two properties. Let's capital lambda be the CDF of lambda in 0, 1, the cumulative distribution. A point in the Veto core must be a point which I think you can call a perfect quantile, a point where the accumulated number of people up to A is equal to the size of the interval 0, the mu of the interval 0A. And that, of course, typically, if your cumulative distribution is not flat, you know, it will cross the diagonal several times at 0, at 1, and 2 other points. But there is an additional condition which makes that sometimes it's yes, sometimes it's no. What's the additional condition? This tells that the distribution function, the CDF, sorry, when you come before A is bigger than 2x minus A, and after A is less than 2x minus A. And what this means is that essentially, you see, 2x minus A, if I am at, it's here. If I am at this point, the curve from one corner to the other is the CDF, right? And it crosses here. Here I say yes because I compare the way the distribution arrives there with the line 2x minus A. And the line 2x minus A is the line of slope 2 passing through this point. So what I'm saying is that you should have a density which is below 2, the density, which is the derivative of this function, is below 2 before we arrive at this point, and still below 2 after. Meaning that these points are not too busy. Meaning that next to this point, there are not too many people. But here, I drew the thing so that the cumulative distribution starts with a slope more than 2. It means that, in fact, here, maybe it's a small group, but it's very intense. It's a dense place. So then I reject that one. But this one I don't reject. And this one I reject, and the other one I don't. Yes. Thank you. Okay? So it's I think, you know, for this NIMBY problem, it's really interesting notion, you know, this idea that we will not be able to choose. You're going to have a multiplicity, but a meaningful multiplicity. Like, you know, in the previous example, you had 4 choices. Here, in this more abstract one, you have 2 choices, and you have reasons to eliminate the extreme, which have nothing to do, of course, with the majority idea. Okay? So, yes?
Why, in your beginning example of NIMBY, why 0 is the point? Because there is like a positive mass of agents, and it's like exactly 2. Why they don't veto 0 out?
They don't, because it's exactly 2. It has to be eliminated. You have to be more than 2. Okay, strictly more than 2.
But what if there are no intersections that have a slope at least 2?
But there is some that there is always some that will intersect with less. You have to have a fixed point. Yeah. Thank you. So theorem. That's the in fact, the most important systematic new stuff, which has nothing to do with the discrete model before. If both the set A and the preferences are convex, in addition to continuity, then the Veto core is also a lower hemi-continuous choice rule. It is connected. It is a connected set because, you know, on the one hand, you have the Pareto frontier, which in this case is connected, and you intersect the Pareto frontier with these with a series of inequalities on the upper contours, which gives you immediately a convex set. Okay, and moreover, you can find a single valued selection of the Veto core, which is going to be continuous in the lambda and mu and monotonic in preferences. And the way you do that is because in the constraints of the Veto core, everything except the Pareto frontier requirement corresponds to a convex constraint on the set. And then you have this set which is convex and nicely behaved with the continuity of both in both directions. And then inside that one, you maximize, you find the Pareto optimal improvement within that set. Okay. So what remains to be done is, of course, to go a little deeper and try to find a single valued selection that is more appealing than the other, and also to develop more systematic application, for instance, to context in which there is a cost to shares, and the set of public decision can be multi-dimensional and so forth. But so far, I mean, you know, these things are suggesting really that the Veto core approach is going to be meaningful in more new context outside the standard traditional role of social choice. Okay, thank you.
One question.
Yeah.
To be commonly heard.
Thank you. In the case where you had your single peak preferences, the Condorcet winner is strategy proof. I mean, you have a strategy.
Yes. Yes.
So what about the veto rule? You have some incentive, at least for maybe prudent strategy, it looks like, no? Or
Good question. I never thought of that. Yeah. It's not. Cannot really be strategy proof because, well,
no, not strategy proof, but
one
good.
has to define. Yeah, no. In fact, there are results by Kondratiev and by Alexei and Janowski who show partial strategy proofness, but in terms of the correspondence and when you are optimistic or pessimistic, yes. You know, this sort of thing works, absolutely. But since it's typically not single valued, then that's all you can get. Yes.
Okay, thank you.
Thank you.